and plenary speaker, Professor S.A. Haider, sir, to please take their place on the dais. We are honored to have with us Professor K.M. Soni, sir, from Amity University, Noida, as our session chair. Professor K.M. Soni, sir, is a Deputy Dean of Domain Engineering and Technology. Professor Dr. K.M. Soni, sir, did his BE in Electrical Engineering and ME in Control and Instrumentation from Motilal Nehru National Institute of Technology, Allahabad, and PhD in Electrical Engineering from Jamia Millia Islamia, a Central University, New Delhi. Dr. Soni is a professor in Amity School of Engineering and Technology. He is having more than 24 years of teaching and research and academic administrative experience. He is author of many books. We welcome you, sir. I now request Professor K.M. Soni, sir, to kindly introduce our plenary speaker, Professor S.A. Haider, sir, and invite them to deliver their talk.
Thank you, Chief. I am very pleased to introduce today's speaker, Professor S.A. Haider. He is a senior professor and honorary scientist A of Plenary Science Division. His current research interests include atmosphere, ionosphere, and magnetosphere of Mars, aurora and air glow emissions in Martian atmosphere, chemistry and macromaterial material in the lower ionosphere of Mars, and completely dust and coma. He was awarded with ISRO Merit Award in 2017. He is elected as a J.C. Bose National Fellow. He has been a president of Plenary Sciences AOGS 2012-14, a chairman of Planetary Sciences Division at PRL 1618, chairman of C3 Subcommission on Planetary Atmosphere and Aeronomy 1822, also as a main scientific organizer, OD COSPAR Event C 3.2, Planetary Upper Atmosphere, Ionosphere and Magnetosphere between 18 to 22. He is also a member of many professional societies, including Asia Oceano Geosciences Society, Indian CAWSCS program, Indian Mars Mission Study Team of ISRO. He was awarded with postdoctoral fellowship from Russian Academy of Sciences in 1989, Japan Society for Promotion of Science Fellowship in 1999, Institute of Space and Astronautical Sciences Fellowship in 2000. So I will not come in between you and today's speaker, and I will invite him to deliver a talk. Thank you.
Thank you, Professor Soni, for kind introductions. And without wasting my time, I would like to thank to Professor Sunita and Professor Jain and Professor R.S. Pandey, who invited me to give this talk. Okay, thank you. And also I would like to thank to all of the members and youngers who is really important for us to carry out this type of research. Okay, so no, previous. It's okay. It's okay. Maybe it is a general audience, so maybe 1 or 2 minutes I will tell. overview of science and explorations of Indian planetary mission. We are involved in the Indian planetary program at PRL from 25 years or 30 years so. So, actually, in the beginning, Professor Bhandari initiated this program in 2008. Before that, he was collecting the moon samples and analyzing the samples at PRL. After that, ISRO realized that they should explore a mission on moon. And after long discussion and so many argument, it was decided to go on moon. And 2008 it was sent. After that, again, we thought which will be explored for Venus, Mars, and other missions. In all exploration programs, I was the member of that committee, and how it was passed from the ISRO and we got the sanction. It's a very complicated process, but I will explain in a little bit. So next one, please. So exploration of the solar system and beyond. This was our idea. The current technology and anticipated indigenous development in the decades will allow us to meaningfully explain. This is the thought of the ISRO. So, but who will do these things? So it was initiated by PRL, because PRL is doing the basic science, and other laboratories of ISRO, remaining 12 or 13 laboratories, they are technical. So they are making the payload. But PRL is also making the payload and giving the reason why should we go for this planet or why we should not go for this planet. Okay. So now here is, you can see the moon, then Mars, Venus, asteroid. And so initially we have the thought that we should cover all these things. Next, please. Development needed. For this program, we decided that development is needed. Development means activities initiated. And then hardcore rover, robotics, lander, sample returns. These are the important points which are required for planetary science in the case of moon and in the case of Mars also. Because the planetary exploration is only possible when India can give some outputs. So ISRO is ready to give, but which type of payload, which type of exploration we need, PRL comes into the into the picture. Okay, this science is required. So now, spacecraft processes for the long-term mission. Next, please. Now you can see here. Indian Planetary Exploration Program was initiated by Chandrayaan-1 in 2008. As you know, it was a very successful for 2 years program, and we got data from the Chandrayaan-1. Then it was decided, okay, we should go and complete the remaining studies of moon. So Chandrayaan-2 was explored in 2019. Again, then Mangalyaan, MOM-1 in 2013, it was launched, and where I was very much involved because Mars is my subject. So I was told by the Professor Bhandari and Goswami, all these people of PRL, and even ISRO Professor U.R. Rao suggested me that we should start something for Mars. So we started in 2013, the first mission on Mangalyaan. Okay, very good. So the first mission, Mangalyaan-1, MOM-1, it was explored in 2013. Now the next mission, which I will tell something here again, Mangalyaan-2 will go approximately in 2031. It is almost approved. And then Venus mission in 2028, it will go. Probably maybe 1 or 2 years here and there, because this is a very typical thing. So, but it will go, it has been approved, and chairman of ISRO has already announced the Mangalyaan-2 and Venus mission. Next, please. In order to, for the exploration of moon and other missions, we need the rocket. Now PSLV, it was first generated and it reached up to the moon. But PSLV cannot carry big payloads. So finally, when I was the member of this committee for the exploration in ISRO, so I was told that 25 kilogram payload it can carry, and you prepare for the 25 kilogram. So out of 25, we prepared for 6 to 10 or 8 kilogram payload. But finally, in the end, it was told that it cannot carry 25, and 13 kilogram it can carry. So many things were removed. Now I am coming here, GSLV. GSLV is a big rocket, and now it has been tested. Now Mark III, it has been tested, and Venus, Mars, and other missions for carrying the heavy payloads, maybe 25, 30, or 45 kilogram. Next. Now you can see here Chandrayaan 1. Chandrayaan 1 carried these payloads, and one is, you can see the solar, wind monitor, impact probe. It was proposed by R. Sridharan, and this is the neutral mass spectrometer, which was dropped from the moon. Moon is the orbit is at 100 kilometer. From the 100 kilometer, it was dropped. So in situ, neutral density was observed on the moon surface between 0 to 100 kilometer by this impact probe. Now here it is a SENA instrument, and this is the neutral analyzer. Radom is the radiation, LLR altitudes. TMC, this is the camera by SAC, trained camera, mapping camera of the moon. And M-Cube, definitely Goswami published a paper in Science on M-Cube at that time, SIR2 and Minisar. Some of the payloads came from the abroad. I will tell you which country. CIXS X-ray spectrometer, high energy X-ray spectrometer, and HI-C. So some of the payloads were made, developed in PRL, and 5 payloads from other countries. Can you show the next? Now you can see here. So this mission Chandrayaan 1, 22 October 2008, it was liftoff. Lunar capture 8 November. Lunar polar 100 kilometer circular orbit. It's a very difficult because there is no gravity on moon. Therefore, circular orbit was possible. But in the case of MOM-1, it is elliptical orbit because gravity is there. So we cannot come close up to 100 kilometers. So we don't have the data up to 100 kilometer on Mars. At Mars, we have the data around 500 kilometer minimum altitude or pre-axis. So release of the moon, as I said, this is the Sridharan instruments. It was released, and first time we got the neutral mass spectrometer spectra from this, and Chandrayaan 1. Concerning the payloads and lunar observation 16 onwards, and end of the mission 2009, of course, about 2 years. And this is the receiving station at Bangalore. Whatever the data is coming in GSN net antenna, it receives 32 meter long. It receives the data and provides the data to us. Next, please. As I said, Chandrayaan 1 mission payload, you can see here, 5 payloads were Indian. 1, 2, 3, 4. Name I have already given, LRI, high energy spectrometer, and this. And 2 collaboration between Switzerland, Swedish, and Indo-UK. One Indo-UK, one Indo-Swedish, these 2, which is Sara. And Sara is, Barabash is there, one of my friends. He developed this payload, and of course I was also involved for getting the final collaboration with Sweden for Sara, with the ISRO people. CIX X-ray spectrometer. At that time, we were unable to develop this spectrometer, the wavelength 1 to 25 nanometer or 1 to 10 nanometer, whatever. But after that, we decided that we should develop this instrument ourselves in our PRL laboratory, which is done, and in MOM-1 it was sent, I think. Now M-Cube is here. This is the collaboration between Germany and Bulgaria. Minisar, radiation means which is coming from the sun, and then in the environment of the moon, it is taking the observation of the radiation at the high energy, SIR2. This is also the collaboration. Next. Okay, after Chandrayaan 1, successful 2 years data Chandrayaan 1, we decided remaining data, remaining instruments, some of the instruments could not work also, I should report here, but most of the instruments work nicely. Chandrayaan 1 mission demonstrates the Indian capability that planetary exploration is possible in the inner solar system. Outer solar system, it is difficult, but ISRO is trying. We need the rocket. Payload we can provide, but without rocket payload cannot go. It carried a suite of payloads, 3 of which were first of their kind, performing remote sensing studies of planetary body. All payloads on board performed as per specifications. It is mentioned here, but some of them, 1 or 2, did not perform. Major discoveries and new outstanding. Discoveries, whatever the Goswami did, actually they proved whatever the data from the MQ that OH is possible on moon, and the hydroxyl ion and hydroxyl neutrals are there, so there is a clue for the water. Now, cited now breaking example of the international cooperation. So we should appreciate that many foreign people were ready to collaborate, and ISRO formed a committee and their payloads were checked and assessed. Then they decided 5 payloads from the other countries. What is the next then? Suppose Chandrayaan 1 gone. Next is Chandrayaan 2. Next please. Remote sensing observation from orbiter and intensive investigations localized area of high scientific interest. Mission objective: realize and deploy the lunar lander rover and lander not provided, not carried by Chandrayaan 1. So next understanding that we should send the next mission Chandrayaan 2 with lunar lander and rover capable, which happened in the case of Chandrayaan 2, but it was not successful. You know very well, I think everybody, Chandrayaan 2 rover was not successful. But Chandrayaan 3, it was successful, same rover, I will come there. So carry payloads in the orbiter that enhance the and add to this scientific objectives for Chandrayaan 1, because below 100 kilometer on moon we did not know anything. That's why the rover and lander is required. So ISRO agreed, and they started to make the lander and rover, and our duty was to develop the payload for the landing site of moon, which happened in Chandrayaan 3, and in the dark side, polar region, it was first time it was sent Chandrayaan 3. Technological challenges, what is? Orbit management, intelligent auto navigation, realization of the robotics and rover. Because robotics and rover, first time we got the results from the rover and lander on moon, on Chandrayaan 3. Now the same technology we want to apply for the case of Mars. So the rover and robotics, all these things. But it will, in the future, people are thinking it should not be only orbiter, it should carry the lander and rover. In the case of Mars. Environment, thermal vacuum, next. Now you can see here, Chandrayaan 2 configuration. Here, this is the orbiter, Chandrayaan 2, and this is rover in Chandrayaan 2, which was unsuccessful, and here again lander craft, it was unsuccessful, but the same both instruments were used in Chandrayaan 3, and orbiter was the old Chandrayaan 2, which is working still. And so it was used in Chandrayaan 3, and we are getting the data from Chandrayaan 3, very good data of the volatiles on the surface moon. Next please. Here you can see here Chandrayaan 2 carried, this is the camera, it was developed by SAC. Image infrared spectrometer, also SAC. Synthetic apertures are, and also SAC. And now you can see here a large soft X-ray spectrometer. As I said in my previous PPT, this X-ray spectrometer, it was developed from PRL now. Earlier it was collaborated from abroad. Neutral mass spectrometer, Chase 2 from SPL, and alpha particle detector, you can see here, 1 to 25 kV, it was developed by PRL, and its data is coming. Laser induced breakdown spectroscopy, LIPS, by other people in LEOS in Bangalore. And lander payloads, it has been decided, which was failed in Chandrayaan 2, but in Chandrayaan 3 it is successful. And Chase, successful in Chandrayaan 3, we getting the data. And one point I can add here, in Chandrayaan-3 through the chest, we have got the data by thermal properties of the lunar surface. Few centimeters, if you go below the surface, temperature change significantly, which suggests the observation, but reason we do not know why it is happening, and such a gradient of the temperatures on the surface, it is very high, and when you go down, it is very low. So Langmuir probe for measuring the surface plasma density, SPL proposed, and they are getting the data. Radio occultation experiments for measuring the total electron content from SPL. Next. Now you see the new data of the XSM. As I said, X-ray spectrometer measurements around moon, and the data is coming from solar minimum condition to solar maximum condition. Very good data is coming, and it is published in one of the best papers, and many data are coming. You see, this is solar flare. Solar flare is emitting from the sun, and then it is reaching, and this is the moon surface. So this data is obtained here. Next. Exploration to Mars, MAM-1. MAM-1 carried, as I said, we were not allowed many payloads, so only these 4 payloads, and 13 kilometers, 13 kilogram or 12 kilogram. So lab, Mars camera, methane sensor, because at that time and even now, methane, whether Mars has or not, it's not known. So this is payload was decided. Thermal emission spectrometer, this is also decided for the measuring the thermal and energy. Next, please. You can see here methane sensor, SAC, Martian exospheric composition, main ka Dr. Anil Bhardwaj is involved here. This is his payload, SPL. At that time, he was the director of SPL. After that, he came to PRL and became the director. Thermal imaging spectrometer, this is SAC. Mars color orbiter, SAC. Lyman alpha photometer, this is a very high energy there in the atmosphere, which is coming for the dissociation. LEOS. Next. Indian Mars mission MAM-2, we propose. Here we are coming into the picture. Our department is coming into the picture. After that, we decided that we should write a proposal for Mars 2 mission. And earlier, ISRO told that by 2022, it will go then increasing. Now this is 2030, 2031. And it will go that way as approximate. And the payloads has been almost decided. Can you go next? Now, the orbit of this MAM-2, very interesting, which we propose actually, I was involved here, this is my figure. That orbit should be, because I was told by the ISRO that the spacecraft cannot come below 500 kilometer. It can come up to the 500 kilometer, then it has to elliptical orbit and 50,000 kilometer, very far away from the surface of Mars. But definitely, we want up to 200 or 250 kilometers. Maybe they can decide. We have proposed that 250 is enough for us, but below 250 it cannot come. So now you can see the orbit here. If we get the 500 kilometer and this 50,000 kilometer, then all solar wind interaction processes you can get here. This is the bow shock, magnetosheath. This is happening. Earlier it has been measured. And magnetic pile-up boundary, magnetic pile-up, plasma sheath. So these red lines, this is the proposed orbit of the MAM-2. So if it passes from here, so plasma sheath can be discovered, then magnetosheath plasma can be discovered, and in this you see this is very close to the atmosphere. So the ionopause or atmospheric height can be observed, and magnetic pulse. So these are the names which can be discovered if we get at least 500 to 50,000. If we get 250 kilometer, definitely we can go deep and deep into the atmosphere of Mars. Next, please. You can see here this is the shock position 1.5, radius of Mars to 2. Can you go previous? Now you see 1.5 to 2 here. Okay, next. Then again you see the terminator bow shock 2.5 to 2.7. Can you go by? You can say this is the terminator. This side north, this side south, and you see the situation 2.5. Next. So we can get the data here. Solar wind speed becomes slow when it reaches the bow shaft, crossing the bow shaft. After passing the bow shaft, solar wind velocity, it is actually 600 kilometer per second. It becomes 400 or 4.5 kilometer per second. Magnitude thick boundary, inner boundary, terminator 2000 kilometer, there we can study. Ionopath observation 3 to 400, it has been reported, but discovery of my next paper you can see. Yes, go to that. So this is the payload now slowly we are progressing, and particularly my department is progressing. Planetary Science PSDN, name of the department is PSDN, Planetary Science Division. Proposed experiment from PRL for Mars mission. Langmuir probe, it measures the electron density in situ. So whenever the spacecraft move in any orbit, electron density will be measured along the spacecraft path. Radio occultation experiment, this is also developed and being developed, and Dr. Varun Sheel is involved, and Pabari is also involved here. They are developing in my department. Retarding potential analyzer, another person from my department. MODEX, Pabari is also involved, I think Pandey knows very well. So he is developing the payload, and today his experiment is going to ISRO for the launch of the PSLV. So test the MODEX that it is working really or not. It was definitely proposed at that time when I was the chairman of the department. Magnetometer is required for study of this thing in atmospheric field, because magnetometer gives the magnetic field in Bx, By, Bz. What is the role of the magnetometer in the atmosphere for measuring these electron densities and RO and LP? So this is when we propose, and these missions, these payloads are approved for the MAM-2 mission. Next. LP, this is the electron density range, 10 to the power 6, you know very well. Electron density in the case of Venus and Mars, 10 to the power 5. So this is very good, and we can get 40 nanometer, these dimension cylindrical. We have time, no? I will try, but not in 5 minutes. It was started late, I think. Okay. So now weight of LP sensor is 100 gram. So it's a very small, tiny instrument, and it can be carried from the MAM-2. Next. This is for the electric field. So electric field still it is not measured. So we need to measure the electric field, and that's why this instrument has been finalized by the ISRO. And for the electric field is one of the most important instrument for the ionospheric electric field. Next. Now here you can see here that this is a new thing. Recently it has been published in 2023. So once you propose the experiment for the planetary exploration, let us say LP, let us say magnetometer, let us say, then before getting the data from the ISRO, we should use the earlier published data and get the new science whether we are able to do or not, because after getting the data, we don't want to listen from our people that we do not know how to interpret this data. From the raw data, I am talking from the raw data to the useful data. So that we analyze the raw data, and this is the LP data, which we have proposed. That's why I am showing this PPT. LP we have proposed. From the already mission, we have taken the data and analyzed this thing, and we were able to publish this data in high altitude ionopath. So whatever I have mentioned, 300 to 400 kilometer ionopath altitude, actually if you analyze in deep, so that is not true. Now you can see here, this is the very high altitude ionopath, and then this is a 500 kilometer, this is 1000 kilometer. Again you can see here something, and 600. So this ionopath altitude, as expected, it is varying, but nobody expected that it can go 1200 kilometer or 1100 kilometer. So one way, somewhere here, the electron density is suddenly cut off, but some other time, some other latitude, longitude, it goes up to 1500 kilometer or 1200 kilometer. Next please. This is the radio occultation, and this is the basic physics of what we can get from here. We can get the electron density. This is a remote sensing instrument. Challenge for the future is to observe the diurnal. Still, we do not know the diurnal variability of the electron density, because from the satellite, diurnal, because I don't have much time, otherwise I could have exercised. Diurnal means from morning to evening or from morning to the next morning, 24 hours. So in this 24 hours, a spacecraft can move from this location to the other location. So 24 hour data, it's not possible to pick up. So it is very, very difficult. Only the surface measurements can give the 24 hours regular data. So till now, diurnal variability is not known. But if we are getting the circular orbit almost for RO, then most of the time it will pick up, it will impact with the atmosphere. So ionization can occur very close at interval of the time, let us say 1 hour, 1 hour, 1 hour. So 12 or 13 points we can get during the diurnal variability. So that's why this proposal was accepted. Next. Now the RPA is for the ion density, and RO is not for the ion density, that is also only electron density. Here you can see the O2 plus, CO2 plus, and next please. This is one of my colleagues, Pabari, Mars orbit, I am also there. So dust is actually, this very interesting payload, because dust is not measured IDP. Interplanetary dust particles. These dust particles beyond 500 kilometers exist everywhere, sometimes in the circular orbit, sometimes along the spacecraft. So we can get this thing, we can get the flux, IDP flux. From the flux we can model all these things. So this instrument is developed for measurement. Now one question is again here, so ISRO asked why you want to send for Venus, why you want to send for Mars. Do you think IDP is changing for planet to planet? Yes, it is changing for planet to planet. So anyway, but the result will give the correct information. Next. Development of the magnetic is BX, BY, BZ. Next. Exploration of the Venus, it is expected 2028. I cannot read, but anyway. Neutral ion mass spectrometer. Importance of this spectrometer, I can tell you. Neutral mass spectrometer, I think most of the Pandey, you know, Americans, NASA, they are sending. But their payload is little bit heavy. We want to send this payload very, very small, 500 gram. Reason is that if this proposed Venus ballooning mission is proposed, then it can carry only few kilograms. Maybe I think 4 to 5 kilogram total weight. So for that, we may be given only few gram. So 500 to 800 gram. In PRL, people are able to develop up to 800 gram neutral ion mass spectrometer. It can measure neutral at the same time with the interval of, let us say, millisecond difference, ion. So you can assume that neutral and ion produced at the same location, let us say latitude, longitude, so there will not be significant changes, though it can measure the neutral density and ion density simultaneously. You can see here the dust analyzer, Pabari thinks. Lightning experiment, I think it is very important for us, and Pandey is here, so he is working. Radiation monitor, this is the whatever the high energy radiation monitor, and Shanmugam of my department, he is doing X-ray monitor. Shanmugam, he has already developed and it has been explored, and we got the data which I have already shown there in previous PPT. Now here, maybe it will go or not go, because there are comments. We have received the comment, and comment is serious. Venus ballooning, we want to propose. Several presentations we gave from the ISRO chairman. Initially they agreed, but finally now they are telling it can carry only very limited payload. Therefore, so many expenditure and effort after that what we will achieve. And balloon is a technology which can move along the Venus, maybe I think 4 hours, 3 hours. So only 3 to 4 hours, 6 hour data. And only one balloon from Russia, it was successful for 4 hours. After that it torn and destroyed. So, but for this we are making the neutral mass spectrometer, because this neutral mass spectrometer, through the balloon it can observe, because the spacecraft cannot come below 100 kilometers. If you see the data of all the missions below 100 kilometers, spacecraft can never come down. And there is no radar which can measure. In situ requirement is there. Therefore, we can see here the only balloon is the technology from where we can get the in situ measurements, ion density and electron density, which can be provided by the neutral mass spectrometer. You can see here the dynamics of the meteorology and Venus next. Lightning, maybe Pandit ji gaye? Acha. Now Pandit ji. Lightning on Venus, as you know, Pandeyji, lightning on Venus is a major topic of investigation regarding the planet's atmosphere. Unlike Earth, Earth we have the water droplets, we get the lightning at about 10 kilometer, cloud is there. Venus has clouds at 40 to 60 kilometers away, maybe 70 kilometers here, significantly higher compared to Earth. This is one difference. The clouds are, and here is the sulfuric acid cloud. In the case of Earth, it is H2O cloud. So the chemistry is different, which is not known at all. These clouds are primarily composed of H2SO4, Venus clouds, and which generate centric charges in the similar manner. How H2O? H2O is discharged, H2SO4 is also discharged. It makes the sulfate ion and hydrogen ion, it makes oxygen and hydrogen. Okay, now these molecules play a crucial role in the electrification process on Venus cloud, leading to the generation of the static electric charges through various mechanisms. Next. One indirect method, now it is very clearly it is mentioned by the C.T. Russell, who is indirect method of detecting the presence of lightning is through the propagation of the Whistler waves. We can detect the Whistler wave, but still there is no guarantee that lightning occurred at that place or not. But there is the indirect measurement if we are getting the enhancement or boost in the magnetic field. Whistler mode waves are characterized by the high frequency, low frequency, and low frequency and circular polarization. Thank you. Magnetometer on board Venus Express. Now here again you see that we have analyzed the latest data. Before sending the lightning instrument Pavari. Pavari is moving here and there because it has to be proved whether really we are getting the data that is good or not, and it can be analyzed so many things. So many people are involved in my department, 60 people are working on planetary sciences. Magnetometer on board Venus Express is useful to detect such Whistler waves in Venus atmosphere. This magnetometer has a sampling rate of 128 Hz. Please remember these things, Pandeyji. Hence, it can measure waves up to frequency of only 64 Hz, these things. Next, please. Now, here one thing important which we are thinking, because I am also involved here. So now you see the Whistler wave mode from here low solar cycle, minimum solar cycle to maximum solar cycle. It has been analyzed solar minimum period, solar maximum period by C.T. Russell group. But here one thing you see, whatever the expectation was that the solar maximum or minimum should be, one should be less or more from the others, but it is not happening. You can see here, almost in the same, but still we need the analysis. Next, please. Now, how it can occur? This is the very well known schematic diagram of the Venus magnetos. In this region here, you see where actually in the case of Earth, neutral sheath is here, plasma sheath is here, and whatever the IMF field going here and coming here. So we can get the very VLF waves, and we can get the Whistler wave in this region, and here it was the hyperbola like things which I will show you later, and this from here and from here, and that hyperbola, then hyperbola from here, this, and below also. It can give you the propagation of the Whistler wave. Next, please. Yes, now you can see. This is the position. This is the position of the magnetic field, IMF field. This IMF, this, and you see here, the Whistler wave is moving here. So in this region, it is happening, and from atmosphere to ionosphere, there is a possibility that the Whistler worm can be detected. This is the case of Earth because it has the close field lines. Next, please. Yeah, this is the new result which is not published, and we are planning to submit in GRL. Pandeji. So this is the Bx, By, Bz. We have taken the measurement from the Venus Express. Here you can see we have used the filter of the background of field, background of the ionospheric field or whatever. This is the only Whistler wave field effect. And you see here is a 0.2, 0.3 point, and here it is a 20 nanotesla or something. So most of the fields are reduced from here by using the filter. This filter has been provided by C.T. Russell. We are using this filter, and you can see here significant enhancement is here. But in the Bx compound in the x direction, no. In the z direction, very less. So here we are getting. So VLF, or you can say Whistler mode, can occur at this time here, and reported the presence of this. And now here you can see the 42 to 60. This 42 hertz to 60 hertz, it is selected filter because magnetometer has this frequency. Within this frequency, any limiting range, you can say, we have taken here. Next. And now if it is occurring, then you can get the holograms. Now this holograms, if you see here, this part, this is very close to 0, something here, and also magnetic field there, it is belonging to this region. But here there is no magnetic field expansion, there is no expansion. So before and after, you cannot get effect of the Whistler mode propagation. Here also you can see no effect, very less, little bit, and then again negligible effect. So it confirms that the intensity, or you can say our work is going to be close and proving that this Whistler mode exists, and this measurement is taken at 400 kilometer, which is required because this magnetic field loops, which you are saying hyperbolic loop, at 400 kilometer occurs, not at 100 kilometer. Next, please. Now, again, I would like to say in few minutes, Emirates Mars mission, which is, I am collaborating with these people. I visited to Dubai and AUS and some other institutes also in here. And you can see the spacecraft position. Next, please. And this is very interesting orbit, and it covers here very long orbit, and there is, these two moons are there, and we are getting here the next, please. This is the result of the EMIRS. You can see how the image is formed. This is the Hellas region, and this is Argere region. There are two basins. You know the basins on moon. Moon basins, if you go several hundred kilometers, you can go down and down. Same thing happening here in the case of Mars, and this is basin, depth is 7,000 kilometers. And this is 7,000 or 700 something. Anyway, I can confirm. This is a little bit less. So these two regions are very important. And you see the characteristics of the pressure. This is the pressure, surface pressure. So when you go down and down, the pressure will be high. When you go up and up, pressure will be low. So here pressure is high. You know that the pressure of the Mars is 6 to 7 millibar on an average. Next to. Now you can see. Here you can get very interesting, this is unpublished result, we are planning to Nature Astronomy. You can see here. This is the Hellas region, this is coordinate. When you see the data of the Hellas region at this coordinate, and this is Argere region, which are two basins on the surface of moon, on surface of Mars, are 6.5 millibar. So why it is increased? Because of the basins. There is no increase here. And this is the northern hemisphere where is no basins. Because of that, this is seasonal changes. Next. You can see here the pressure, seasonal variability of the pressure here happening. Next. This is in the southern hemisphere, northern hemisphere temperature as usual is different, but you can get changes, dip and crest. Next. Now the conclusion. To participate and propose, this is my idea, of course I can suggest many things to my staff members, to participate and propose a new mission, payloads for planetary sciences. This is our objective of planetary science division. Recently we have proposed a sample return mission from moon. Still it is going on, so many fightings. So to carry out modeling of satellite data obtained from planetary missions, whatever the data we will get, definitely we will make the modeling, we will do the modeling. But before that we should start the modeling research on those type of instruments. So because of that we started, actually Varun Sheel is taking care of, because after my retirement, we started the modeling group. And then every year, 3 months, we are calling to the summer trainee students only for planetary sciences modeling. And they carry the data and all these things, they go there. We actually develop a computer center in PSD in Thaltej. Anyway, now, not analyze the data, please, last I think. To analyze the data of planetary atmospheric sciences using remote sensing technique, because only remote, because in situ it is very difficult. There is a possibility, this is also markable, to explore a lander with MAM-2 mission. Since we have got the technology and proved the technology for Chandrayaan-3, so lander is possible. ISRO is thinking seriously to explore a lander with Mars-2 missions on the surface of Mars. Let us see. It's not final. It's not final. We have sent the name of the experiments which we want, science from those instruments on the surface of Mars. I think 18 instruments we have sent the list. To understand the science of forthcoming data, future Indian planetary mission, we should analyze the NASA and ESA data before getting our Indian mission data. Thank you very much for patience. And
Sir, due to paucity of time, we cannot take the questions from the audience.
okay.
If can we take? Yeah, very brief, please. 1 or 2 questions. I just given the time. So 1 or 2 very brief questions, please.
Yes. Very difficult, because the instrument, I can tell you, I am a very, because when we proposed the methane experiment, MSM, we thought that enough methane is there, but enough methane is not. So the minimum limit of the instrument, it's a limit. So we could not get any methane density or methane results from our existing. We need to develop very, very low intensity, very precise, which was not done, because there are some things. ISRO is asking the payload, give me payload, give me payload, give me payload. Yes, this is happening, and people they don't give the money. Immediately money they don't give. So they give the money later. Okay, so because of that, actually we are also facing the problem which is hidden. Any other questions? Which? Actually, the magnetic field intensity. Magnetic field intensity.
Which light source we are using? Source of light.
Source of
Laser light, LED light, or general.
Not LED, probably, because.
Very small. 40
Yes. No, this is actually US development, 40 to 60. This is not ours.
Okay, not 80.
Not I agree, fully agree. Next.
Sir, I have a question which is not directly from the scientific perspective, but we are the host institute and many of our students
You can
are
ask any questions.
Yeah. So how
I am
this-
ready to give reply,
because we
maybe
have
more
to
than 1 hour for the question.
So we have to sync our academic curriculum. Our students are interested in what ISRO is doing, because everyone was excited with Aditya mission or Chandrayaan.
I did not say Aditya because I am not the solar physicist.
I got it. So we have to sync, and many students are looking at the opportunities which are available at PRL and other institutions, undergrad and postgrad.
Okay, one shortcut method.
Yeah.
They can collaborate with the PRL people and PI. After some time, data will be freely available. Generally, ISRO holds the data for 6 months, for Moon 6 months, for Mars 6 months, or maybe 8 months, whatever you can, maximum 1 year. After that, nobody can stop the data. It is freely available like NASA. So, your students, you and other people, they can go the website of the ISRO and download the data and use the data. Then you start discussion with PRL and SAIC and whatever you want. That is very simple. This is very clearly, this was actually last week, there was a meeting, academy meeting. So I am the member of the academy. So I went there and Pandit ji jante. So this was the questions by a senior people. Ki data sharing issue with the academy president Ashutosh, who was the DST earlier, and then Ashutosh. So he told some of the people oppose that there is no sharing. Even I oppose that sharing is not there. TIFR told that there is a lot of telescope is there and at different places. After 6 months, this data was provided to foreign country and many people are using. So this is not true that sharing is not possible. Sharing is possible. You find out the way and go to the ISRO and ISRO website or even TIFR website, whatever. And for PRL thing, definitely we are directly connected with the ISRO. You can ask from ISRO. Immediately they will give you reply. No questions? Okay.
Dr. Haider is available here. If further anybody want to ask, they can ask in between in break.
During the break you can ask.
So Dr. Haider, thank you so much.
Actually, especially I want the questions from the students. Because my time slowly gone. Your time is coming. You have to take care of the exploration or ISRO's or our Indian programs at least. Indian programs. Without you, we cannot. So don't depend on the internet. And do the science properly and go to the depth. Then it is possible.
There is one more simple, very question regarding the sulfuric acid cloud.
Sulfuric.
How could you just measure that it's a sulfuric acid cloud?
Sulfuric droplets actually from the spacecraft, they have neutral density is available in the data, NASA website. H2SO4, sulfur, because this is different planets. We know that this is sulfuric acid, neutral density, clouds. So from there we can say so many observations from the neutral density of H2SO4. So neutral density H2SO4 is like H2O is there in the cloud. There also from the neutral, and from the ground-based observations, you can also check that the sulfuric acid in the total contents is there or not.
So dear students, you can interact further if you want so in the break. Thank you, Dr. Haider. Indeed, it's a very good talk, very good talk, very informative, very interesting and motivational for the students. That's why myself is concerned. Thank you so much.
Thank you very much. Thank you.
Thank you, sir, for such an informative and motivating speech. I'm sure it will be beneficial to all our listeners. I now request Professor K.M. Soni, sir, to felicitate Professor S.A. Haider, sir, with a memento.
हो जाए मुझे तो पता ही नहीं कि ये बाकी है.
I also request Professor Sunita Ratan ma'am to felicitate Professor K.M. Soni, sir, with a memento. Thank you all for your time and attention. We would like to invite you all for third technical session at different parallel venues F3 Seminar Hall, F2 Seminar Hall, and F3 MDR. Thank you so much. Attention, please. Please keep your phones on silent.
Very good morning to one and all, dignitaries, invited guests, delegate, faculty members, and dear students. We welcome you all to the technical session third of the 6th International Conference on Recent Trends in Materials and Devices. I welcome all the dignitaries, session chair Dr. Andras Sapi, and keynote speaker Professor Rajiv Mehta, and invited speaker Dr. Raghuvendra Singh Yadav. We are honored to have with us Dr. Andras Sapi, an associate professor in chemistry at University of Szeged, Hungary. His diverse research interests encompass CO2 activation, flue gas treatment, size-controlled nanoparticles, 3D mesoporous oxide supports in surface chemical processes, battery research, and photocatalytic CO2 activation for water treatment. With a prolific academic career, he has authored over 100 publications, accumulating a remarkable total citation count of 2359 and achieving an impressive H-index of 27. His impactful contributions and innovative research make him a significant figure in the field of chemistry. Please join me in welcoming our esteemed associate professor, whose work continues to advance our understanding of critical issues in chemical processes and environmental sustainability. I now request to kindly introduce the keynote speakers and invite guests to deliver their talk.
So good morning, everyone. Thank you for the introduction. So it's my pleasure to chair this morning session, and we will have 5 great talks in the morning. So 1 keynote speaker and an invited talk, and also we will have 3 presentation after it. So let's start with the keynote speaker. So Dr. Rajiv Mehta, it's really nice to meet you, and then thank you for coming. And then just let me give a couple of words from your credits, and then you can give us your talk. So Dr. Rajiv Mehta is Distinguished Professor of Chemical Engineering at Tapar Institute of Engineering and Technology, boasts nearly 3 decades of exceptional achievements and awards. Renewed for his groundbreaking work, he has significantly contributed to diverse areas from the development of graphitic foams to pioneering research in polymer nanocomposites. His impactful projects have direct implications for national defense, enhancing seawater resistance and protection armor against fast projectiles. Dr. Mehta's contributions have garnered prestigious awards, including the Best Innovative Young Researchers at ICON 2017 and the Gold Trophy and Plast India 2018 for the category Breast Research in Polymer Science, Technology and Engineering. As the head of the Department of Chemical Engineering, he has completed 7 research projects, guided numerous students, and ventured into entrepreneurship, winning the 3rd prize in a Venture Lab weekend in the Netherlands. With 67 peer-reviewed international publications and leadership roles, Dr. Mehta stands as an eminent figure in chemical engineering and polymer sciences. celebrated for his outstanding achievements and recognition. So please, Dr. Rajit, please come and then talk us about, the special concrete structures. Please, the floor is yours.
Can I have the pointer?
Pointer, laser pointer?
Yeah, laser pointer.
Yeah. Or you gonna
it's
speak
not,
from
yeah.
here? Maybe let's try.
No, just, okay, that's fine. Yeah, please.
Okay, and then maybe otherwise.
Use that as a
Yeah,
pointer.
but
Thank you.
I don't know. You wanna use this?
No, I will not use this. Well, good morning to all my colleagues and dear students. I will be talking about this topic, which is quite a mouthful. Actually, what the talk is about, we are trying to prevent corrosion in a metallic bar by application of a polymer epoxy coating containing different forms of nanofillers and checking the corrosion properties in an accelerated mode. So my talk is all about this. Okay.
It's working. It's working.
Okay,
Just
yeah.
try.
Yeah, it's working.
Don't push. Don't push. Just.
Just one, yeah?
Don't push. It's always working.
Okay,
It's
okay.
like this.
Thank you, thank you. So, I am talking about assessment of nano-reinforced epoxy coatings in press. Okay, got it. Epoxy coating for enhanced corrosion protection or inhibition in reinforcing bars in concrete structures. So, I'm Rajiv Mehta. I'm looking after a center we have at Thapad in a collaboration with Virginia Tech USA, and I'm looking after that center also. I'll just talk very briefly about the center in 2 slides after this slide. And I'm also looking after the Department of Chemical Engineering. I'm a chemical engineer basically. So in this project, my team consisted of Professor Shruti Sharma. She is in the Civil Engineering Department. Professor Rooplal Mahajan, he is a chair professor of our center, and he's a professor at Virginia Tech USA. And all the work has been done by our student, Nikhil. He is a senior research fellow in the center. So let me introduce my center in just 2 slides. So this is a Center of Excellence in Emerging Materials at TIET. So this was born out of collaboration with Virginia Tech in July 2019, about 4.5 years back, with Professor Mahajan selected as the first inaugural chair professor and myself as the first coordinator. So what do we do at the center? It basically started with the technology of producing graphene derivatives from coal, from Indian coal, bituminous as well as anthracite. And then we moved very quickly on to the projects involving applications of these graphene derivatives, basically graphene oxide and multilayer graphene. And I will just read out some of these projects. So they include, application include nanocomposites, sustainable construction, corrosion prevention. My talk is just on this, one of these projects. Sensors, we have humidity sensor, physiological, food quality, precision agriculture sensors, catalysis, antimicrobial composites, wastewater treatment, modified pavements, and it's a long list. And besides the graphene derivatives applications, we have also starting our foray into other 2D materials, and unrelated to this, all this as a platform for development of cure and diagnostic of cancer. Okay, just a few stats about the center, just to give you a holistic idea how big or small it is. So we have our own building, And number of ongoing projects in which we have a research student are 45 ongoing. A lot of seed money projects. We have 40 GRF and SRF, 3 PDFs. Number of our Thapad faculty involved in the SEAMS activity, 75. And so far we have produced 65 high impact SCI publications in 4 years, out of which 2 years were gone because of COVID. Okay, let me come to my talk. Introduction, actually this talk is about corrosion protection. And if a lot of you must be remembering, yesterday in the first plenary lecture, Dr. Narayanan had talked about corrosion, the basics of corrosions. So one very small element out of his talk is what is I will be talking about and what our study is all about. So corrosion is clearly a very is a villain, and it's one of the prevention is one of the biggest challenges faced by the construction industry worldwide, and billions of dollars are spent for retrofitting, repair and rehabilitation. Reinforced concrete is one of the most widely used material for construction, but it is also responsible for 10% of the CO2 emission in the world. For every pound of cement which we produce, we evolve 0.9 pounds of CO2. So anything which helps to reduce the consumption or increase the longevity of the concrete, that is very welcome from the environmental point of view. So the standard textbook approach is you coat the metallic bar or a cylindrical rod or a flat surface with a polymer. Polymer typically used is a cross-linked epoxy. So, and especially to prevent corrosion in harsh environments. Harsh environment means near a seashore or in a chemical industry and so on. And this epoxy contains of two components in general, resin and a hardener. After mixing and polymerization of the resin and hardener, a strong film is formed that provides an almost impenetrable barrier once fully cured. This figure shows the epoxy coating. Epoxy coatings have good mechanical strength, durability, excellent resistance to chemicals and good thermal resistance. So what is the problem? There are two major challenges in using ECR, epoxy coated rebars. First is the epoxy is a thermoset, is a strong backbone. So it's a very brittle polymer and substance. So inherent brittle nature of cured epoxy thermoset coating leads to micro cracks or damage. You know, when you unload the epoxy coated rebar from a truck, or when you are fixing it up, or even when you are making it up. So because of brittle nature, it can't take any impact. So there might be some cracks coming in. And second challenge to address is the presence of some inherent micro pores in epoxy coatings, which occur during their fabrication and which can lead to enhanced corrosion and catastrophic failure. And because, you know, when you cure a thermoset, you go through a region when it's very viscous. So whatever trapped air is inside, it will be very difficult to take it out. So these two challenges, how to address them? First solution is inherent brittle nature of epoxy can be modified by making it more pliant or impact resistance by introducing ductility to the epoxy coat using the nanofillers. And the second challenge, solution 2, is we can micropores in epoxy coating during fabrication can be taken care by using self-healing techniques. This was also briefly mentioned in the plenary lecture, but the technique which we will be using, the mechanism is totally different. A very brief synopsis of the nanofillers. This is single layer graphene, all of you know this. This is multi-layer graphene or reduced graphene oxide. This is graphene oxide functionalized, graphene oxide as it is. Then single wall CNT, multi-wall CNT and monomolinite clay, natural clay. So then you have organically modified clays and so on. And with regard to the self-healing, second challenge, we have used microcapsules based self-healing smart coatings which provide automatic recovery and extend the durability of coating without external intervention. What we do is, the mechanism in the picture you can see here, a crack is here and it is filled up by the self-healing capsule contents. This very briefly is the mechanism, how it's supposed to work. So these circles are the microcapsules containing tung oil in this case. You can use different other compositions. You see this crack, when it is coming towards, it hits the microcapsule. There are a lot of microcapsules spread all around. So the crack hits the microcapsule, and because the crack is very sharp and very small, it will rupture open the capsule, right? The crack has air in it, and due to capillary action, because it's very small in size, the tung oil contained in the microcapsule will be sucked in the crack, and some of the air of the crack will transfer to the capsule. What happens is, in presence of air, the tung oil polymerizes. So it effectively, you can see here, it will make that crack free of air and full of solid material, and it will basically stop the crack of propagation and fill up the crack. So how to process this is a very standard mechanism. You take your nanofiller or nanofillers, put it in the epoxy resin, high shear homogenization at 24,000, 20,000 RPMs, then ultrasonication using a probe, then you add the hardener for 10 minutes stirring by mechanical impeller, and you have a coat ready to apply to the metallic surface. And then these coated bars were subjected to accelerated NDT testing. So we did two type of corrosion studies were undertaken. In the first, we had bars. See this black bar, cylindrical bar. This is in a simulated seawater, and then you have bars embedded in concrete. So we put both of these in seawater, simulated seawater, and studied the corrosion. How to study accelerated corrosion? Two methods we had taken. One is the ultrasonic guided wave monitoring. Second is the corrosion current measurement, and of course visual inspection when the corrosion starts. Actually, when corrosion starts, it will turn into iron oxide powder, and that will push against the coating. So it's very easy to see that it has started. And to validate the findings obtained through NDT, the coatings were subjected to destructive testing for tensile strength and other properties, and mass loss by weighing it. Chair, how much time I have?
Sure. About 8 minutes.
8, thank you.
7 minutes.
Okay. So our results and discussions. This ultra-guided wave signature of corroding bars were continuously captured from our own setup, NDT setup, and the degree of degradation of the bar was indicated by the transmitted signal strength compared to the healthy signal, shown here. Actually, you try to waveguide a wave through your material, and if there is any disruption, any corrosion, any holes, that will deteriorate that signal on the receiving end. So you get a fair idea of what the state of corrosion in your bars. Similarly, we have this peak-to-peak voltage to quantify that, and this is the results. On the left, you can see the peak-to-peak voltage, that signal voltage, wave-guided voltage, wave voltage, and you can see the bars in solution on the left and in concrete on the right. The one nearest to the ordinate y-axis is the without coating sample. So under these conditions, our signal, our current and our voltage, a normal steel bar, iron bar, will start corroding in 7 hours, which normally would corrode in 4 to 6 months or maybe much more years, would start corroding in 7 hours, and by a few days it's totally almost gone. The next one is epoxy coated. It is also better than the uncoated, of course, but still within few days it is also gone. Then we have nano fillers. We have nano clay incorporated in epoxy, and that is this blue line. This is much better. Actually, clay, what it will do basically is increase the tortuous path for the ingressing ions. So it takes longer time to reach the bar. And this one in pink is putting micro capsules just by themselves. It's very impressive. And the one in green, which is showing no corrosion, is a blend of graphene oxide and carbon nanotubes. On the right also, it is embedded in concrete, curve shift to the right, as the ions have to pass through the concrete also. And a very similar trend is seen by corrosion current, right? So all I want to show here is that in self-healing composition pink, this, you see the corrosion starts to happen, current goes, it increases, then that mechanism comes into play, the cracks are plugged, and the corrosion current drops to almost zero again during the running of the NDT. And to corroborate those, we did some destructive tensile testing, and they fit exactly what our NDT told us, techniques told us. GeoCNT is again average Mohs loss is almost zero. Let me conclude. The addition of GeoCNT to epoxy coating results in high quality protective layer that efficiently prevents corrosion for a long period in steel substrates or reinforced concrete structures located in harsh environments. The presence of functional groups on basal planes of geosheets helps entrap the aggressive ions and provides an effectively impervious network. I would like to point one thing out. We experimented with a lot of coatings, lot of nanofillers with different combinations and all that. So I'm not showing those results here. They are all published. I'm just showing for one, GeoCNT. And one more thing, our uncoated bar starts corroding in 7 hours. Normally uncoated bar would go for even years in a not harsh environment. And this GeoCNT is still going strong after a year and a half, which means if you translate it loosely into actual results, we might have solved the problem of corrosion for good. Of course, there are some assumptions involved, but it will go in lifetime. And second, the conclusion was the presence of nano-disperse fillers also drastically reduce the diffusion of ions or water by making their diffusion path more tortuous. This is well known in the field. Additionally, self-healing coatings such as MC coating have also been found to have the ability to effectively halt the progression of corrosion in situations where the corrosion has already been initiated. Non-destructive testing methods are well suited for measuring the long-term corrosion progression. These are well established in metallic substrate, and we have sort of modified it for our purpose. And finally, nano reinforced coatings would have great impact in terms of increasing safety, that is very important, and overall service life of composites and RC structures by drastically cutting down on the repair and maintenance cost. These are the publications with this study itself. So all our civil engineering journals, we had tough time. If we send it to polymer journal, they say you send it to civil engineering journal and and vice versa. But anyway, we got them in good impact factor journals, about 7. These are among the highest in civil engineering journals. Finally, it happened. Also, we find a patent on this, An acknowledgement is research is funded by SEAM Center at Thapar Institute. Thank you very much for your patience.
Thank you very much. Professor Rajiv, thank you very much for your really interesting talk. So we have time for 2 questions from the audience. Please go.
Yeah,
Okay,
please.
Thank you, sir. It was very good, informative lecture. I have one simple doubt. How do you ensure, how do you practically do nano dispersion of these nanofillers in the
Yes,
epoxy?
that is very important. Actually, sir, we start with epoxy resin, which is a low viscosity resin. Viscosity is important. We pour our nanofiller, put it in that epoxy resin. We do 2 steps. One, we take a homogenizer, and in the inner shaft rotates at a maximum 24,000 RPM. Or we typically operate to 20,000 RPM, which is a very high speed. So what that does is that breaks the fillers into microscopic size particles. That size, once we achieve, we put it in a ultrasonicator probe, which is enabling very high energy density in a small volume. So we normally, to share the conditions, we ultrasonicate it for about 10-20 minutes. Then we again homogenize it and again ultrasonicate it. And over the years, we have seen that this does lead to nano dispersion, as borne out by indirect property measurements and even temp measurements and other measurements.
Thank you, sir.
Okay, yeah, I'm sorry that I skipped there. The inner content I told you was tung oil, which polymerizes in presence of air, and the outside is phenol formaldehyde shell. Actually, it has to do 2 things. It should not break when you are studying at 20,000 RPM, and it should break when the micro crack hits it. But this is, I will not take credit for it. It is pretty well documented in literature. So there is a particular recipe, you follow that, somewhere between art and science, I would say. So it works. Even a second, third trial, we were able to get it working.
Sir, actually, I saw the results. Actually, there is mismatch in the Young's modulus in case of this metal rods in the epoxy. Epoxy resin, if you are using, epoxy resin have Young's modulus around 1 gigapascal and metal rods have more than 2. So actually first we need to match the Young's modulus, because if we are using low Young's modulus material on the surface coating, when we will apply the load, it affect the complete crack in the structure. So first challenge that you said, like slowly the cracks generate in the structure, and according to that, first, otherwise we can use thermoplastics also instead of epoxy.
Yeah. Okay. See, as far as strength bearing capacity is involved, like they are used in civil construction and all that, major load or almost all the load is taken up by the bar, which would be 1 to 2 centimeters in diameter. The coating, on the other hand, may be 20 micron in thickness, 50 micron thickness. It is not going to take the load. Load will be taken by the bar, but thermoset Young modulus is, I mean, it's not compared to metallic, but compared to thermoplastics is much better.
Okay.
Young modulus.
Okay.
But the problem is the impact. Impact goes
Okay,
on.
we need to-
It is so rigid that it doesn't yield. So whenever there is small impact or a high impact, it tends to crack. So we want to take all the good properties of epoxy and try to, better the deficiencies.
And the second challenge, sir, like you said, the pores generally comes in the, when we prepare the coating of the epoxy. So by addition of these nanofillers, how we can control these pores?
No. For pores and the
Or-
cracks, we are relying on the microcapsules.
Microcapsule, that oil is coming. Thank you, sir.
Okay, thank you very much. I think
Thank you.
you can follow this. yeah, the discussion in the tea, and then give another hand to Professor Rajiv. Thank you. Thank you, Professor. That's very nice. Okay, and now we are. So now we are moving to our invited talk to Professor Raghavendra Singh, who is a distinguished senior scientist and researcher at the Center of Polymer Systems, Thomas Bati University in Zlín, Czech Republic, which is close to Hungary, huh? Since October 1st, 2017, Dr. Yadav has been actively engaged in a groundbreaking research focused on lightweight, flexible, low-dimensional, electromagnetic functional nanocomposite materials, incorporating advanced elements such as silanes, benzene, graphene, and magnetic nanoparticles as nanofillers in polymer matrices with a focus on practical applications. With a prolific career, Dr. Yadav has authored around 75 publications in reputable international journals, showcasing his expertise in material science and nanotechnology. His impactful works has garnered significant recognition with a Hirsch index of 27 and an impressive citation count of more than 2,000. And then we now will have a listen to a talk about a lightweight and flexible nanocomposite for electromagnetic shielding. So please give your talk. Thank you.
Thank you for introduction. Thank you for invitation by organizing committee here, especially Anup Gupta sir. Good morning to all of you. Here I will talk about advanced high performance lightweight and flexible nanocomposite for electromagnetic shielding and microwave absorption application. So here I am working in Czech Republic. It is an European country near to Germany, Poland, and Austria. And here we have a Thomas Bata University in city of Zlín. And this Thomas Bata University consisted of various departments. In this university, we have a research center. It is Center of Polymer System, and we are working on different research directions, including nanomaterials and advanced technologies. In this research center, we have a biology lab, chemical lab, physics lab, and a technology lab. There are spaces for microscopy lab. So here in this talk, I will talk about EMI shielding and microwave absorption, and then design strategy of ideal EM wave absorber materials, advanced polymer nanocomposite as EMI shielding material, polymer nanocomposite and characterization, result and discussion. You can also follow one reference book. It is on advanced nanocomposite for electromagnetic shielding application. So recently it is noticed that there is an increase of electromagnetic radiation in the atmosphere by electronic devices, and it can something wrong with that, please. And these electromagnetic radiation can influence the working of electronic devices, and also it can influence human health. Therefore, we need a shielding material, microwave absorber material, which can control this electromagnetic pollution in the atmosphere. Do you have pointer also? So we need a electromagnetic interference shielding material. So it should have a strong absorption, broad absorption frequency bandwidth, thin thickness and flexibility, high thermal, mechanical and oxidation stability, easy processability, low cost and long cycle life. It can be achieved by advanced polymer nanocomposite. It has good flexibility, lightweight, easy processability, chemical resistance, and also ultimate scalability. It can be achieved as a polymer nanocomposite. So we have developed this polymer nanocomposite using a thermoplastic polyurethane as a polymer matrix with a spinel ferrite magnetic nanoparticles and conducting a reduced graphene oxide as a nanofillers. So we have developed spinoferrite magnetic nanoparticles by sonochemical methods, and here you can see sonochemical synthesis condition was around frequency 20 kilohertz, power 70 watt, and sonication time 60 minutes. We have also developed a reduced graphene oxide by reducing graphene oxide using vitamin C as a reducing agent. We developed spinel ferrite magnetic nanoparticles and reduced graphene oxide. They are used with thermoplastic polyurethane, and they were mixed together, and we did melt mixing by microcompounder under this condition 200 degrees Celsius for 7 minutes and 150 RPM speed, and we got our nanocomposite, and it was hot pressed, and we got nanocomposite sheet. And here you can see prepared nanocomposite sheet, lightweight and flexible. Here you can see ferrite nanoparticles X-ray diffraction pattern and cobalt ferrite and doped with zinc ion, and it was noticed that crystallized size was decreased with addition of zinc 2+ ion, and it can be associated with influence of growth rate of these nanoparticles when these cations zinc 2+ ion was added in the solution during sonochemical method. The presence of X-ray diffraction pattern connected with spinel ferrite nanoparticles in nanocomposite can be seen, which confirms the presence of nanofillers, spinel ferrite nanoparticles in the nanocomposite, and there was no separate diffraction peak of reduced graphene oxide, which is associated with fine dispersion and small size of the reduced graphene oxide. The Raman study shows presence of characteristic Raman bands associated with vibration of cations at octahedral and tetrahedral site in spinel ferrite nanoparticles. The characteristic Raman band of reduced graphene oxide and graphene oxide can be seen in Raman spectroscopy of these graphene oxide and reduced graphene oxide. Here in this nanocomposite Raman study, we can see presence of reduced graphene oxide Raman peaks and presence of spinel ferrite nanoparticles Raman peak in the prepared nanocomposite, which confirms presence of nanofillers in TPU matrix. Here we can see absorption bands in FTIR spectra related to vibration of cations at tetrahedral and octahedral site in spinel ferrite nanoparticles. Here we can see a reduction of functional group in the reduced graphene oxide in FTIR spectra of these reduced graphene oxide. Here we can see characteristic Raman characteristic absorption band of the TPU matrix here, which confirms presence of TPU. We also did a TEM study, and we noticed that prepared spinel ferrite nanoparticles were 7 to 15 nanometers in size. And here we also made some study of a nanocomposite, and it shows that There is presence of spinel ferrite nanoparticles and reduced graphene oxide in TPU matrix. Here you can see a magnetic hysteresis curve of spinel ferrite nanoparticles, and with addition of zinc 2 plus ion, non-magnetic ions, the saturation magnetization was decreased. Further, here you can see electromagnetic interference fielding effectiveness. This one is the total one, and it is associated with absorption and reflection. We have also made a study of real part of permittivity with frequency and imaginary part of permittivity with frequency. And here we can see Kule plot, and it shows different semicircles which are associated with different interfaces present in the prepared nanocomposite. We have also made a study of real part of permeability with frequency and imaginary part of permeability with frequency. And here we can see dielectric loss, which is a ratio of imaginary part of permittivity with real part of permittivity. And this dielectric loss was associated with dipole and interfacial polarization losses. Relaxation and polarization and relaxations. And here magnetic losses was also studied, and it was a ratio of imaginary part of permeability with real part of permeability. And here in this range magnetic loss was associated with eddy current loss, and in this range it was associated with natural resonance. So here we have calculated eddy current loss by this relation, and we notice that in this frequency range, this value it is constant. It means in this region the magnetic loss was associated with eddy current loss, and beyond that magnetic losses was associated with natural resonance. We have also studied skin depth using this relation, and we notice variation of skin depth of various nanocomposite with frequency. There is one important parameter. It is attenuation constant for shielding material. It depends on dielectric and magnetic losses. So we have evaluated using this relation, and it tells the level of propagation of electromagnetic waves inside the nanocomposite, and it was highest for this set of sample. Further, we have also evaluated impedance matching, which tells level of entrance of electromagnetic waves inside the material, and here you can see a variation of impedance matching with frequency here. So here we have developed a polymer nanocomposite consisted of spinel ferrite magnetic nanoparticles and reduced graphene oxide. When there is an incidence of electromagnetic waves, there is a reflection, there is absorption of electromagnetic waves, and possibly transmitted of electromagnetic waves. So the absorption of electromagnetic waves was associated with dielectric loss and magnetic losses inside this material. Dielectric losses was associated with dipole polarization and interfacial polarization, and also there was a conduction loss, and it was associated with hopping of electron and migrating electrons. There was a magnetic losses. It was associated with eddy current loss and natural resonance. So here in this talk, I discussed about advanced polymer nanocomposite for electromagnetic interference shielding applications, and recent results on high performance, lightweight and flexible thermoplastic polyurethane-based nanocomposite with spinel ferrite nanoparticles and reduced graphene oxide as a nanofiller in thermoplastic polyurethane matrix. I acknowledge my PhD students working with me, scientific group members, collaborators, and funding agency. Thank you very much for your kind attention.
Dr. Yeraf, thank you very much for your impressive talk. We have time for a couple of questions. Before I would go with one. So, when you use these ferrite structures, how could you be sure that these nanoparticles were, kindly dispersed and they were not aggregated inside? Did you use some kind of surface modification of the nanoparticles? And number two, so how the density was increased for the polyurethane foam for this, so what was the concentration you have to use when you had the electrical shielding, effectively?
Okay, it is connected with dispersion of small ferrite nanoparticles. So during preparation, we have taken small ferrite nanoparticles and reduced graphene oxide and TPU. We didn't use all together. In a melt mixing method by microcompounder, we have taken a small amount of this spinel ferrite nanoparticle, reduced graphene oxide, and TPU in different parts, and put in a melt mixing. It was melted. Again, we put again in microcompounder. So we filled a whole set of a microcompounder by small parts, so that there should be a proper dispersion of nanoparticles in polymer.
Do you have also proof of this, maybe with scanning electron microscopy, or?
If you will put all spinel ferrite nanoparticles and reduced graphene oxide and TPU together in a microcompounder, all together, then dispersion can be a problem. Because they are, melting all together.
Sure.
And maybe in some part there will be more fillers, in some part there will be less. But if you will divide these whole set in very small segments, and then you can put melting, again edit.
Okay, that's
so
great.
Then
and the concentration, where it's effective?
We did around 20% of fillers. These things, and it was maybe reduced graphene oxide. It was around 5%, so it was fine. And maybe another question.
Yeah, that's it. Yeah, okay, so it increased a bit the weight. So maybe a couple of application could be changed due to this, but yeah, but it's good. So other questions from the audience, please.
I have a quick question, small question. So you had used graphene oxide, right?
Yeah, reduced graphene oxide.
Reduced graphene oxide.
Yeah.
Are there any reasons you didn't try using graphene oxide?
Actually, I tried both. I have one publication with graphene oxide, and when we did a microcompounder at high temperature, around maybe 200 degrees Celsius, we have possibility in the microcompounder that atmosphere was something different. Maybe sometimes there are release of gases by melting of polymers, and they can influence functional group and these things. Maybe they can reduce it. So it was converted in reduced graphene oxide. So I worked with graphene oxide also and published separately, and this was something different.
Thank you.
Sir, actually, this you have not shown the result of EMI shielding, like how much the dB, the radiation your material has shielded.
I have shown it. You can take a look again. So here I have shown total around 50, about 50.
Okay.
50 dB.
Okay, 50 dB.
Yeah,
so, what was the concentration here of RGO?
It was 5%.
5% is too high, huh? And what was the optimal result value of this? By varying the concentration of RGO, so you have checked or not this?
Actually, we noticed that there will be a variation in shielding properties with change of these fillers. And here we have a constant reduced graphene oxide, and there is variation here also, maybe constant I have taken, but in another study of filler variation with polymer matrix, we noticed that if we will increase filler amount up to maybe 35% and TPU matrix, then we can get highest. But here we need also to consider mechanical properties. Maybe at higher concentration of filler in TPU matrix, we will start to lose mechanical properties. So if we want both things keep it in good conditions, so we need to optimize it at what condition we are getting best shielding properties as well as mechanical properties. So if we will go maybe 50% of fillers, maybe we will lose our mechanical properties.
Thank you, sir.
Can I add to that actually? What we have seen is that for mechanical reinforcement, normally you go up to maybe 0.1 weight% or for mechanical reinforcement, normally the optimum value somewhere 0.05 to maybe 0.2 weight%. But for EMI shielding, to get to percolation threshold and all that, you need to go to higher concentrations. And at those concentrations, I don't think it will be nano-dispersed. Even theoretically, after some percentage, it's predicted it will aggregate to some extent. So it's a difficult scenario to get best of both things, mechanically also, shielding also.
Yeah, there is a lot of chances of agglomeration, maybe at higher concentration, and formation of maybe micron-sized particles. However, we are trying how to do best, maybe with something managing nanoparticles and TPU, maybe in different maybe methods, maybe solution mixing method and this one melt mixing method. They will provide some different maybe product.
Solution will be definitely much more efficient.
Yeah, and because that's because here you need to reach the percolation limit, yes, to be sure that you have a network. But if you have a network, then you don't have nanoparticles anymore. So yeah, but maybe using graphite oxide or maybe carbon nanotubes, we have good results. I think you also with carbon nanotubes, you can reach the percolation limit really easily, and then you put your ferrite structures on them, whatever. But
we are trying to make a best conducting material so that there should be less amount, and maybe it will help somehow.
Sure. Okay, let's give another hand to Dr. Yeraf. Thank you very much for your talk.
Thank you for the informative and interesting sessions. I'm sure it will be very beneficial to all our listeners. We would like to invite our delegates for oral presentation, and the time is 5 minutes for the presentation and 1 minute for question and answer round. And the jury for the presentations will be Professor Rajiv Mehta, Dr. Raghavendra Singh Yadav, and Dr. Rohit Verma. For the first presentation, I would like to invite Ms. P.S. Sugatha from Amrit Vishwavidyalaya.
So, good morning all. I'm Sugata. I'm a research scholar working under Dr. Sudeep Kumar Bhattavyal in Amrita University, Tamil Nadu. So, this work was done in collaboration with ISO Bhopal, and the work majorly focuses on molecular level of investigation of photoluminescence of carbon quantum dots. So, carbon quantum dots is highly fascinated by all the researchers because of its highly luminescent material. And being a carbonaceous material with a size of nanoscale, it is used in many applications because of its tunable property. So applications such as optoelectronics, sensing, drug delivery, photocatalysis, and biological imaging. CQDs, apart from this, it is fascinated by researchers because of its high quantum yield, and also shows excitation wavelength dependent emission, which is a unique property of all the CQDs, and can also emit a wide range of emissions over a spectrum of colors. But even after such a fascinating features, it is still under debate, and that's because of its luminescence origin, whether it is from the carbon core or from the surface functional group or some organic moieties which is formed along with it. So there are many reports which actually focus on high quantum yield but lack an idea about the origin of fluorescence. Once, if we have that particular idea, we can tune the properties and we can even set out for a new applications. Over a period of time, carbon quantum dots was under the debate, and at that point of time in 2015, Chinlin research team said like they wanted to prove the origin of fluorescence using aggregated quenching effect. Later on 2016, researchers said that the structure and the surface moieties actually play the origin of luminescence. In 2017, they said that whatever precursors what we choose while synthesizing the carbon quantum dot, that is CQDs, will alter the luminescence. And late in 2019, they said that more than carbon core, the surface molecules actually enhance the property. This was further proved through edge aminoproteination by a research team in 2021. So our objective was also to put an insight on this debate. So we wanted to synthesize crystal, which is an organic material, which we expect is decorated on the carbon quantum dot. So we plan to synthesize carbon quantum dots along with the crystal in a single hydrothermal setup, and we wanted to analyze both the crystals and also the carbon quantum dots separately, and then so that we can investigate the origin of fluorescence and also simultaneously find the possible application for the same. So here we try to synthesize crystal and carbon quantum dot in a hydrothermal setup, and where we take O-phenylene diamine with phthalic anhydride in a hydrothermal setup at 180 degrees Celsius. And you can see on the right side the image of a autoclave where you have both the crystals and CQDs formed under the same condition. So we tried, as we have two sets of sample, that is CQDs and crystals, we try to analyze the properties of both. So when we did the absorption spectra, we found for the CQDs that there are two sets of peaks, a peak at 280, which is due to the pi-pi star transition, and a broad peak at around 350 to 515, that's due to the aggregates on the surface. Simultaneously, we did emission spectra at 438 nanometer excitation and also a 280 nanometer excitation. And as I mentioned before, it shows excitation dependent emission, so we also analyzed the same, and we found that indeed it shows excitation dependent emission. We also wanted to analyze the same for the crystal, and we did the absorption spectra and found the similar peak at 280. And we also found the emission spectra, excitation spectra with 280 excitation. And we wanted to know whether the crystal also show the excitation dependent emission. Indeed it won't. Yeah. So we also found a normalized spectra where we found that there is a overlapping of the excitation spectra and absorption spectra, which indeed means that there is only single species which is playing a role behind. So as we found the crystals, we tried to analyze it more in an optical microscopy, and we found that it's having a long elongated crystals. And we also did the fluorescent microscopy, where we found that average sizes of each crystal is around 300 micrometer. We wanted to get into and analyze it on the molecular level, and we did a single crystal diffractometry to get the structure and also the packing, and we found that it's a triclinic lattice structure. We wanted to also compare with the CQDs and the crystals, so we did an XRD analysis where we found that almost all the peaks of the CQD corresponding to the number of peaks in the crystal is present, and almost there are peaks in the lower angle, which is a characteristics of CQDs. We also did a lifetime data for the CQDs and the crystal, and we found that the average lifetime is around 2.1 nanosecond. We also wanted to confirm whatever we have synthesized is CQDs, and then we followed a TEM analysis, and we got the TEM data proving that it's whatever synthesized was CQDs. So we could conclude that the grown crystals have an influence on the CQD luminescence, and the observation of both crystal and CQDs, the optical properties are both same. So we could actually use crystal, whatever synthesized crystal as a tool to analyze the property of the CQD. In further, we can also tune the properties of the CQD and also we can set out a wide range of applications. I would also like to thank my research team in Amrita University, Tamil Nadu, and also ISA Bhopal, and also my research funding agency. Thank you.
Thank you very much. It was really interesting. So please have a couple of questions. So you showed the XRD about this carbon quantum dots, yeah, about the last slide. But usually, so for carbon, there is only just, it was a copper K alpha XRD what you used here. It was a copper K alpha XRD what you used here. So if you go back, there were a lot of sharp peaks, and I didn't understand how they are coming from. If this is, we're supposed to just see something at 26, yeah, the carbon 002, but you have a lot of peaks over there. So where is this coming from?
We expect that the carbon quantum dot actually is decorated with organic moiety, so that can also contribute. That's what we are expecting.
Yeah, but it's not supposed to be coming from XRD because, usually these organic moieties. And how can you get rid of these organic moieties? Because you said there is organic moieties could be, or it can be coming from the surface or the inner core structure of the. Yeah. So how can you separate these three?
Like you can, if you heat it in very high temperature, I guess these moieties will get degraded. But we didn't do that. What we did is we dried it, made it into powder, and then further we did this powder XRD. So I guess there might be some influence of this organic compound is what I guess.
So what is the future plan? How do you want to improve your work?
I just want to, if possible, if I can tune, then I can use it for sensors like metal ion quenching or other sensors like halogenated sensors. Because recently when I was finding out the application part, and I found that it is a good halogenated sensor. So as halogen is carcinogenic in nature, so we can use it as a good halogenated sensor is what we are planning for.
Okay, thank you. Any other questions? Oh, yes, just one more questions over there.
So at what pH have you collected this fluorescence data?
So we didn't check the pH as such, what we have used DMSO as a solvent because it was insoluble in water.
But it is important to focus on the pH effect on the surface moieties. I think there are many research papers which have shown that pH also plays a very important role.
Yeah, there are, but our major focus was we wanted to know whether it's originating from carbon core or the functional group, on the surface. So we have tried to synthesize the same crystals made of same organic compound. So So
what have you concluded? Is the fluorescence coming from the surface?
Yeah,
or from
we concluded that it's coming from the surface, which is decorated by this organic compound, because almost we could synthesize this crystal made up of the same organic compound, and both were showing the same data of optical
so
properties.
what type of function groups are present at the surface?
We did the FT. Sorry, I haven't attached that data indeed. So I guess I have to look onto it, sir.
That will be a very important point to focus on.
Yes, sir. I've already have done the analysis.
Okay, just one thing. You have not shown any scale here. What is the size of the particles?
It's actually 50 nanometers, sir. I'm sorry I didn't expand this.
50 and 50.
Yeah, 50.
50 quantum dots, fluorescence. Anyway, it doesn't go. First of all, second of all, how do you measure the TM? What kind of grid you have used over here?
Gold.
Gold grid. Okay, there is no carbon coating. Yes, carbon coated is not there.
Actually, I'm sorry.
Okay, no problem.
Just a small question.
Yeah, sure.
How did you experimentally segregate or get the CQDs?
Sir, when we synthesize, we expect that whatever sample is having CQD. So, the supernat, and it will be in a solvent form. So, we expect that is having a CQD. So, that for confirm.
How did you process it? How do you cook it out?
We actually dry that solvent thing, and then we can get it into powder form.
How many people do you dialysis and different techniques?
Yeah.
Okay, thank you very much. Okay, so our next speaker is Anita Singh from OMLab. Yes, please. Our next speakers are here. Oh, it's here? Okay, please come. Perfect.
Good morning, everyone. Myself, Anita, and I'm pursuing PhD with my guide from MIT University. And my guide name is Dr. Sangeeta Tiwari, ma'am. I have the introduction of my topic of this fast and drug method. I have developed one method. It's a drug method optimization of selected some antibiotics, pesticides, and some toxic compounds in the matrix of shrimps and honey by using the GC triple quad and UPLC assay with MSMS mode. The introduction of my presentation is antibiotics and pesticides are a group of chemicals that are widely used in the animal crops for protections. So increasing concerns over the presence of antibiotics, pesticides and toxic compounds in foodstuff and the related potential health threats to human. So I have developed one methods through GC triple quad and UPLC with LC triple quad and conclude the validations as per SANTI guidelines. So in recent situations, the present situations demands a rapid turnaround times where the analysis needs to be completed within 24 to 48 hours after a sample is submitted in the laboratory. Thus, it is necessary to have a method by which we can simultaneously determine the target pesticides, antibiotics and toxic compounds in any sample by short methods with equivalent or superior overall efficiency with advanced and sophisticated instruments like UPLC and GC triple quad. I have developed one analytical methods determination of multi-residue pesticides, antibiotics and some toxic non-dioxins PCBs in honey after modifications of some Kucher's methods extraction, and I have achieved the limit of quantification is 10 ppb with some modifications of sample preparation, some modifications of extractions through ethyl acetates. The overall conclude the method was rugged within less than 20% measurement uncertainties or RSD for retention times or area or recovery. The limit of quantification is 10 ppb with the recovery range is 70 and 120 for most pesticides and antibiotics. The methods offer cheaper and safer alternative to typical multi-residue analysis methods of honey. These conclusions, the multi-class multi-residue procedure with LC-MSMS detection has been developed and validated to determine and quantify veterinary pesticide residue in honey. Simple sample preparation method involved liquid extraction, salting out procedures with the help of ethyl acetate with cleanup steps and shortening the sample preparation time. Validation of the method was performed according to Commission SANTI guidelines 2002-657 EC. The method was characterized by good results in terms of recovery, reproducibility, and repeatability along the detection of veterinary drugs and pesticide residues below the recommendation analytical level. Based on these results, LC triple quad method was ethyl acetate extraction showed the suitability of sensitive quantification of veterinary and pesticide residues in honey sample for food safety and application. In these methods, we have developed more than 20 pesticides or antibiotics in a single run within 20 to 30 minutes run. And the short protocol can be replicable to a large number of samples for routine analysis and rapid detections. One of pesticides, Iprodion, are present in most of honey. I think 2 to 5 samples, the Iprodion compound are present. This is the LC triple quad chromatograms with 140 pesticides within 25 minutes. Thank you for attention.
Thank you. Thank you very much. So questions, please. So how can you extract? So did you do some kind of preparation from the honey? Okay, so what? Because it's really important here.
Modified by Quechers methods. It's a liquid extractions and some cleanup steps we have follows, like cleanup with PSA, C18, and MgSO4.
And if you go back to that, yeah. So no, just to the last slide, yeah. No, so to the chromatogram. One more, please. Just one more, please. Can you go one more?
There is one of pesticide analyzed by LC triple quad. So in the honey samples, these pesticides are present in 20 to 25 ppb.
And if you go to the next chromatogram, so yeah, so how could you analyze? Because it's really hard to analyze.
Yes,
yeah?
sir. I have developed the methods with the modification of Quechers through GC triple quad or LC triple quads. In LC triple quads, I have developed 140 pesticides in a single run with LC triple quad, and GC triple quad more than 180 pesticides.
Are you using Agilent?
Yes, Agilent.
So using
both
chem station for this?
Yes, sir. This is the chromatogram from station only.
Okay. Any questions? Okay, if not, thank you very much.
Thank you, sir.
Thank you very much. And then, so we are getting to our last speaker. He's not here? Okay, so I think we are now ending this fruitful session. Thank you all for the speakers and who were here. And then we ready to go for a tea. And then after, please go to sessions. Afternoon sessions will be really interesting. Thank you very much. Oh, and then before that, we give.
I now request Dr. Andra Sapi to facilitate Dr. Raghavendra Singh Yadav with a memento and a certificate. Thank you all. We would like you to invite all for the tea and request you to please join us at the same venue for the technical session 4. Thank you.
देखिए नाम अनाउंस कर दीजिए फटाफट।
जी सर। So we are honored to have with us Professor S.A. Haider, Physical Research Laboratory, Ahmedabad, as our session chair. Professor Haider is a senior professor and honorary scientist A of Planetary Sciences Division, Physical Research Laboratory, Ahmedabad. The primary objective of his research area is to study theoretical aspects of Martian and cometary aeronomy, such as energetic, dynamics, optical and X-ray emissions in the atmosphere of Mars and comets. Professor Haider has served as an editorial and guest editor in several reputed journals. In his remarkable research career span, Professor Haider has won several reputable awards and possessed several publications in national and international journals of repute. I now request Professor Haider to kindly introduce our keynote speakers and invited guests to deliver their talk.
Who is keynote speaker? I should check my.
Okay.
Who is the keynote speaker?
VK Jain, sir. Just see me. Yeah, if you can tell. Otherwise, I can. That's it.
So I should check. नहीं ये तो मैं ढूंढ रहा हूँ. Okay. So Professor V.K. Jain, he is going to keynote address after my few minutes discussion. Professor Jain is a distinguished scientist and professor, Amity Institute of Renewable Alternative Energy. Very good. Dr. Jain has done his PhD in solid state physics from IIT Delhi in 1970. He joined solid state physics laboratory in 1972 and worked as director grade scientist up to 2003. He was head of the Elecon Devices and Micro Electrochemical Mechanical System Division and developed many new technologies. He has published more than 200 papers in national and international journals, edited a few books, and has filed more than 60 patents, including 12 granted. He has received the Technology Award in 2002. He worked as emeritus scientist in CSIR at NPL up to June 2007. He is no doubt remarkable scientist in his field. With this brief introduction, I would like to request to Professor Jain to give his talk. So please go.
Thank you, Professor Haider, Chairman of the session, and good morning to all of you.
So your talk is for 25 minutes, sir.
Okay.
And 5 minutes before, I will give you.
You just tell me, I
So
will
that
stop.
question answer can
You
be
just tell me,
fully
I will stop there, no
Okay,
problem. So the title on which I'm going to talk, this is fabrication of the heterous junctions on silicon nanowires on silicon chips. That is cadmium sulfide. This is P-type silicon for electricity generation from moisture. And second part of this one is also, if time permits, I will take this tin oxide on silicon nanowires on silicon for UV detection. So this is a very recent and new technology because we are working on this photovoltaic systems and all solar cell type of devices, thermal storage for so many long times. Now the concept came that if we go for some other technology, which is a very low-cost technology, that is also required now because there is a big competition in solar photovoltaic market. Secondly, this is not that always we draw the energy from the sun. There are so many other sources from which we can draw the energy, we can convert it into the electricity. So this is a new technology that we can convert even the moisture present in the air, we can convert into electricity by making a junction with silicon. So this is a, we can say that today this is a mini power generator. So major part of electricity is coming from the big plants, we know. Nowadays big plants may be photovoltaic, maybe other sources. Hydroelectricity, coal, gases, nuclear plants, these are the big plants. Then we have gone to this renewable sources. This is solar, wind, bioenergy, geothermal, they are in the process. Now this is requirement now to harvest energy from new other sources. So today they may be a very small source of electricity, but as we have done on solar cell long back when we were making for the space quality for satellites, then we are saying that nobody can think about that it will come as such a cheap source of electricity today, that electricity is cheaper than our regular supply. Similarly, these other sources we are investigating, so today they are a small source, but tomorrow they will become a bigger source of electricity. So in this line, we have this thermoelectricity generation, piezoelectric, triboelectricity. These are also some of the old things now. Now we are coming nano generators, because when we are talking about nano devices, we are talking micro sensors, we are talking about MEMS and LEMS sensors, then it is very important that we should also have a very small source of power. This is, for example, I can give you that in nature, if you go, you want to make a machine of the size of a mosquito, then you need a small power source which can convert into electricity and give the power, then you can make a small flying object. So this type of devices are required now. So how to go? to give power either to sensor or to other things. So in this line, we have this, we have generated electricity. Right, suppose a raindrop is falling. My colleague Dr. Prashant is here, Dr. Abhishek, Dr. Suchita Sen, my colleague in department. We are working on different type of sources for electricity. Like we are converted from raindrop and we can grow a panel of the LED. Similarly, this is a new in the same line that from the moisture we can generate this electricity and we can make a nano generator. In this line, the fundamental mechanism of the science is that various mechanisms have been proposed to explain the origin of this electric power generation. This is due to the gradient of diffusion. This is streaming potential. Something is flowing in this pipe. You can generate power. This is a charge surface from potential we are doing. Moisture enabled is also a promising clean energy source to approach due to the young and waste water present in the atmosphere. The moisture energy conversion due to the diffusion and operation. Without temperature, air, variation, mechanical, any movement, we can generate power from these junctions. So synthesis of a cadmium sulfide, this is a junction on P type of silicon nanowire. So we have to first grow a nanowires. Long back I have done a lot of work in porous silicon, but at that time it was not possible because there were certain problems, but we have made a light emitting diode. But today, other things, when it is coming that on silicon, we are making a silicon nanowires. Although we know that nanomaterials are there in the powder form, so make any device with that, we have made many, but it is not, reproducibility is a big problem. But when we can grow the silicon nanowires on the silicon chip, then we can do something else. So in this silicon nanowires can be easily fabricated using an electrode-less chemical etching process. Then it is a simple, low cost, can be made at a room temperature. This is the advantage. And cadmium sulfide film has also been extremely used as a humidity sensor. This has, everybody knows this thing. Cadmium sulfide thin films over 1D silicon nanowires on array on silicon chip made a chemical bar deposition that we have done here. And we have made a junction of this cadmium sulfide. This is nanowires. Heterojunction has been formed there. So this is a preparation and characterization of the silicon, nanowire silicon on a P-type of silicon substrate we have taken. So it is a pre-clean. We have taken a polycrystalline silicon substrate. We are prepared using metal-assisted chemical etching method technique. So silicon substrate were immersed in this solution. And this is the equation. I am not going to read it, but this is the chemical which we have used to make etching, chemical etching. The oxidation and reduction takes place during this etching process. And this is the formula, we can say, this is the equation, how we are getting this etching of the silicon wherever we have a nanoparticle of the silicon at the top. So we are taking a solution of silver nitrate here, that you can see in this figure. These are the nanowires actually. We have taken the HCM picture of this silicon nanowires on silicon chip. The diameter is here. This is the process that we take fabrication of silicon nanowire. We take a silver nitrate solution, and that formula I have shown that it will come the silver nanoparticle. So wherever you have the silver nanoparticle it will start etching. Oxidation reduction process take place, and depending upon the time, how much thick you want, how much length you want, we can make a silicon nanowire just by chemical etching. You can see I was showing you this picture of this is a nanowires of silicon on silicon chip. The other advantage of this one, you can see here, all this process is going. The silicon has a big problem when we are making a solar cell on silicon. The reflection loss is very high in this region. And in this, when you take a silicon nanowire, then in this case, your reflection loss is very less, and we have seen that we absorption, reflection, it is reduced. Even by texturization is low, but when you are taking a silicon nanowire, it is very, very less. Now this is a HCM, images of as-grown polycrystalline silicon, and we have measured it, the diameter in the range of the nanowires is 40 nanometer to 100 nanometer. And the height is, in our case, we have gone up to 5 microns. So this is sufficient. So instead of making a heterojunction on silicon wafer or making all diodes, all the other structure, we are making a heterostructure with silicon nanowires. So this is the advantage, and this has opened a new field. Not only in the case of this, we are making a electricity generation. We have made a sensor, UV sensor, IR sensor, even you can go terahertz sensor. So this is a thing that we can tailor the barrier height of the material at the top and with the silicon nanowires. So this is a very recent development. And this is a chemical bath process technique. This is a very new technique, ion by ion. It deposits on the surface of the silicon, and we can make like a epitaxial layer just at a room temperature or a low temperature. Instead of going like gallium arsenide, the other thing at a very high temperature, this is just a room temperature epitaxial growth. This again we have shown, this is a temperature, pH, how much we have to maintain in the solution, all the parameters. Sometimes you have to go to very low temperature, sometimes you have to make room temperature depending on what type of silicon nanowires you want. This chemical bond deposition of our cadmium sulfide. So this is now if you will see this cadmium sulfide silicon heterojunction device. So the silicon wafer is there, and we use the metal assisted, and on this we will do the chemical bath deposition of cadmium sulfide. So it is coming at the top, and you can see the HCM pictures in this junctions, this heterojunction. This we have done the EDX analysis about all that making, whether it is present in the same way or not. So you can see that this is the area of 50 micron we have done silicon, this is a cadmium, this is sulfide. So clearly it gives the percentage, and you can see the percentage wise on that. Now measurement has been done in this junction. Measurement up to setup used to measure the output voltage and current. And this is where that you can say when the humidity chamber is there, we put some glycol solution in water. You can go to increase the humidity right from 20-30% to 100% humidity. So actually we are increasing the humidity in the atmosphere. The junction splits the water present in the air, and it gives a electron hole pair in the junction similar way, OH and H. This one I'll show you. And you will get, this is a variation of the current and voltage. So you can see this black color one is a output voltage. This is going to there when we are increasing the humidity. And the red color one is showing the current with the time that it is giving the current. And this thing has improved that when you are putting in a chamber, suppose you put your sample in a 100% humidity chamber, immediately you get a voltage and current. And we have given this time is 50 minutes, it comes down when you remove the sample. So every time you are getting a constant voltage and current. And you will keep it for a long time, then you get a, this is the, you can see from here that the maximum voltage, suppose we have one, so we have given up to 70 hours like that. It is decaying sometimes with a very long time, but it will give you continuous. So if you put this sample generator in a humidity chamber, or suppose you are near in the sea, some city there, you have a high humidity, you can generate power from there continuously with these junctions. So this is we have done a time graph that even we have kept our sample up to 300 days, this one, the samples are working. So it is right now a very small source of power, but you can make an array and we can generate a good amount of power from there. So this is here we have made series and parallel, a combination of that, and you can see that here a light emitting panel is also growing with the help of that, and you can add up on voltage. So number of generators, this is small, and you can make a bigger one. So like that, this is a start of this technology. We can make many improvements, and we can generate power from humidity, moisture. This is because moisture is everywhere, so much plenty, so it is also a good source of that one. This is a energy band diagram. If you go that how it is making a junction, so this you can see this is a N-type cadmium sulfide. We have a P-type silicon here, and this one. And when the water is coming there, you can see OH is split, OH and F-2. So this OH will go there, H will go there and you will connect this positive and negative charge and you are getting a voltage and current. Do you have time?
Yes.
So another, this I have shorted out, but another device with the same, we have made a perfect device because the similar device can be made not only this generator of electricity, we can make a sensor, we can make a solar cell, we can make a visible light, UV light, IR light. We are working all these parameters, only we have to change the material to make a heterojunction, tailor the barrier height according to that. In the same way, when you make a ultraviolet detector, it is only possible in silicon carbide, not in silicon, because band gap is not matching with the UV. And if we take a silicon, 70% is just reflected back, UV. So this is a great problem. And silicon carbide, if you are going to use, then it is a very, very difficult because the temperature when you want to move the diffusion to make a junction is 2200 degrees centigrade. So it was very difficult. So we have given a solution for that, that instead of just going silicon carbide, we can go to silicon nanowire base. So I'm not going to the application of this UV detector. There are plenty of that. But in UV range also, we have 400 to 320, means you can go to DUV from this one, 320 to 280, to UVA, UVB, UVC, and last one is far UV, 200 to 10 nanometer, which is not coming to the earth from sun. So this is also a very requirement that how much UV we are getting because it's very harmful to the skin. Then we use food industry or water purification, everywhere we are using this UV detector. So we need urgently, if a low-cost device can be made. This is high sensitivity, high selectivity, all these parameters we maintain. And fundamentally, I told you that it was possible only if you make a photoluminescence, that is a secondary effect if you want, or you make a Schottky junction with PN, but again the thing is very, very less. But long back, skip it, that when I was doing this in 93, 95, I have done a lot of work of porous silicon. In silicon, at third surface, we generated the third form of silicon. It is a now single crystalline, polycrystalline, multicrystalline, but this is another form that we have made a porosity on silicon. The effort at the time was how we can make a light emitting diode in porous silicon, because till now all LED which you are seeing, it is not silicon based, it is gallium arsenide based. If we are able to make a light emitting diode on silicon, then we can integrate and your computer will become much, much faster because it will be optical communication. So at that time I made the first LED in this porous silicon, and it was announced everywhere that it is the first international observation. But the problem still today exists that the life of this LED on silicon, porous silicon, is short. So still it is a field of investigation if we can make light emitting diode. But same idea we have seen. If you give at the time UV light, it gives such a strong photoluminescence you can see with the naked eye like a coal is fire is there. So much strong photoluminescence is coming when you are putting UV light. So I made use of that in silicon nanowire the same nanostructure is there. And if we can give the UV light, it will definitely sense it. If we can separate the electron hole pair by making any junction, then we can make a UV detector. So using that idea, we have made this one. Again, the silicon nanowires on UV detector, and we have made a junction with the tin oxide on silicon nanowires with a wide band of material. So with this, when we have made the tailor the barrier height of this junction, we are able to get a very good result. And this is again, I am not going to, this is a bare silicon, and if you take a nanowire of silicon, again, the reflection loss in IR region you can see is very small, and now we can make use of that. This is again, we are doing the electrodeposition of this tin oxide on silicon nanowire, and these are the complete structure that EDX analysis of that, how the junction is there, what is the barrier height. We have made a, this is a, then metallic contact is very important. So we have tried to make a metal contact in both the sides, the aluminum, titanium on silicon and titanium aluminum at the bottom. This is required like for the space quality, not for character, but it is a perfect contact when we can make silicon. So with this contact we have made, and this you can see that if you, how the resistance is varying if we are giving a UV light here in time second is so fast, because the switching action in this one is a silicon based, so the switching action in microseconds we can take place, like solar cell. This is a, we are given the diode characteristic, how a diode is working, so we have taken the complete diode characteristic in presence of dark or in presence of UV light. This is again the same property that we have studied this one. And finally, this is the band picture, how it will work. This band picture heterostructure is taking place. So this is a complete theory for that, that how the heterostructure can be made with the nanowires, not only with the silicon. This is again the same diode action we are showing. And this is a device you can see that we have made a perfect meter of this one, integration with the complete electronic signal processing, and we are putting a light, so it will give immediately a response. And at the bottom you can see in the device structure, then sensitivity, responsivity, detectivity, every factor has been calculated for that. So this preliminary examination, this is showing that this has a much better detectivity and responsivity compared to any other one. This is again the comparison of the international data with the other one. And this is the last one, that even we can make a smart chip, silicon chip, that half of the chip we are making a photovoltaic device, this one, from where the sunlight is falling, you are getting a power. And half of the chip we have silicon nanowires, UV detector, so there is no need of powering from outside. It is self-fired, so we call it a smart chip. We can develop for UV detection. So these are my key members. Thank you very much.
Thank you, sir. I think few questions. So dear audience, if you have some questions, still we have time for questions. No questions? It means everybody understands everything.
Agree. Everybody agree.
Okay, let's say again thanks to Professor for a nice presentation and nice talk. And please, thank you, sir, for giving us time. Next speaker को introduce करना है. Who is the next speaker? She is absent, ना? हाँ सर, उनको बोल दीजिए.
I'll introduce ma'am.
So she is?
Yes, ma'am.
Oh, I don't know. Okay, next speaker is Dr. Dheeraj, and 25 minutes presentation, and she will talk, maybe her talk is not mentioned title, I think Nanoscience Department. Dr. Dheeraj Sood currently works at the Department of the Chemistry. Saint Longawal Institute of Engineering and Technology. Dr. Dheeraj does research in green chemistry, very popular, analytical chemistry and environmental chemistry. She has published over 150 papers in the national and international journal of repute. Dr. Sood has authored several books, chapters. She has a remarkable research background with huge number of citations and H-index of 27. So with these brief introductions, I would like to invite to Professor Dheeraj Sood to give his talk. So you have 25 minutes, and just 2 minutes before I will raise the hand.
A very good afternoon to all. First of all, I would like to thank the organizers of the conference, and in particularly Professor Smita Rattan, who gave me an opportunity to express my views and my research with the august audience. So for today, though I am working in broader areas of analytical chemistry, green chemistry, metal organic frameworks, but for today's presentation, I have selected an area that is a functionalized biopolymer, chitosan based, eco-friendly sensing platform for inorganic pollutants in environmental matrix. So starting with why we need to do the study in this area. So I'm just giving some glaring picture, but these are the picture you may have encountered in everyday life. Today, almost 26% of the global population, that's without the water. There is an issue of water scarcity, then water pollution. And the other side, on the right-hand side, the pictures, they are from some of the one of the Punjab river. And the second one is from the Ludhiana, Buddha Nala. And that image itself talk about the imprints of the industrial revolution or industrialization. Ludhiana has a big industrial city with the textile industry, mechanical industry. But the outcome of this is one where this Buddha Nala, once a serene river, it has changed into this setup. This is not the situation I'm talking with respect to Punjab or Ludhiana. And when we talk about the environmental issues, these are not the global issues. Basically, they are not the local issues. They have a national importance as well as a global concern. And one of the concern with our water bodies, right now we are at a stage where we are reached up to our groundwater. So once the groundwater is polluted, everything, we have touched the very basic fabric of life in a wrong way. So mainly when we talk in terms of the chemistry as a culprit, we talk about the influence of the anthropogenic substances. So from anthropogenic substances, for the students' sake, I'm mentioning all these things. Anthropogenic means which is everything man-made chemicals. So once they are introduced into any of the matrix, environmental matrix, nature doesn't know any mechanism to deal with them. So as a result, there is a continuous emergence of these recalcitrant genobatic chemicals. And earlier we are talking about, we blame the industry for the pollution. But now we are at a stage where the pollutant of concern are coming from us. And one of the new emerging pollutants which still are in a stage of development, in a stage of reduction and quantification. These are basically the pharmaceuticals, most of the pharmaceutical, veterinary drugs, and more often is that the chemicals we use in our home, household chemicals, personal care products, they are also now coming big way as emerging environment pollutants. And beside coming from the pesticide, agrochemicals, so the list is long. So just why to go for the research in this area, I'm emphasizing this. But as a chemist, this thing is very dear to me. Like no substance, it is toxic in itself. Poison word is used, but I will take it as a toxic in itself. It is the only concentration of the substance it matters. So, and bigger gap if I see in terms of the understanding of these environmental pollutants from that of the chemist point of view, scientist point of view, as a layman and an ordinary person. Only chemist or the scientist, they talk about concentration unit in a parts per million, parts per billion. But if you know any common man, does he understand these terms? No, he doesn't understand. He talks in terms of the ml of the solution, grams, kilograms, all this. So the basic idea, for a scientist, they deal with these things, but the message is that the concentration of anything we use, which we introduce into the environment, that's very important. So this itself, promote the scientists to find out the green and sustainable materials and technologies for this. And as I said, for this present work, I have selected the biopolymeric materials. So where the word is biopolymeric, so I'm talking about the natural materials. And for this, chitosan is a selected material, that is a versatile biopolymer. Why the versatile biopolymer? One is that we have enough of the cellulose, number one polymer. This is second most abundant polymer after cellulose, available as a chitin, and its deacetylation we made a chitosan. And its Degree of this distillation, it decide about its molecular weight and its properties. And being a renewable source. And third is, I will go back that part later, it is a linear amino polysaccharide which has a glucosamine and N-style glucosamine units connected by beta 1 for glycosidic linkage. And what are the sources for this polymer? This polymer is abundantly available in the marine world, the exoskeleton of the snails and shells we see, and terrestrial world in the insects, outer covering of the crab, crustacean, and even the plant world, the covering of the fungus. So these are some of the sources I reported. So now this versatile polymer, it has been extensively explored for our research in many areas. For example, in this agriculture, for a controlled release of the pesticide or the agrochemicals. And moreover, this material, it is also used as a plant stimulator, being a source of the nitrogen itself. And beside this, they have also had been studied in a food industry for the packaging or as a stabilizer also. And in a biomedical engineering or medical field, it is extensively explored for a tissue engineering, drug delivery carriers, and lot many applications as a scaffolds, and even in cosmetic as a stabilizers. And this material is also studied for the wastewater treatment as a superabsorbent. So basically the idea to develop as a superabsorbent or a material for the wastewater treatment, that is utilizing of this waste, which is only from the seashell, it comes about to 60,000 to 80,000 tons per year. So this much voluminous waste can be used, can be explored for uses as for the wastewater treatment for various of the environmental applications. So some of my work is particularly dedicated to the wastewater treatment, where it has been employed as a superabsorbent hydrogel, simply absorbent, or in various forms. So one of my publications where I have utilized it for the industrial wastewater treatment, taking the textile industries waste, it has been reflected on the cover page of the journal. And another, the patent is published also, where I prepared a super adsorbent from this polymer. And what is interesting at that patent is, it is a self-cleansing gel. So once we impart a properties where we don't need to remove the pollutant from by utilizing some chemical, then it will be always a precious thing. So that patent has already been granted. So little bit now I'm talking with respect to the chitosan as such. Being a biopolymer, it is non-toxic. And then it's biodegradable. Anything which comes from the nature itself, it obviously with the, it's only the residence time, it will be biodegradable. And obviously it will be biocompatible with the living things as well, living organism, as well as for the matrices also. And because it has a diverse functionality, it has a primary hydroxyl group, it has a secondary hydroxyl group, then secondary amine group also, and the primary amine group. So these are amenable to have a lot many chemical modification can be performed with this. So that is in terms of its chemical reactivity. And being a waste, now it is costly again a compound, because once its many uses have been explored, also still we carry it in under the category of cost effective. And once we have a amenable functional group, then obviously for the heavy metal ion, they can form complexes with this. So remarkable chelation property that gives an edge to as compared with others for the adsorption activity. And this particular polymer, it can easily be formed in the form of a film forming. That will be again enhanced its property. And furthermore, all the predicted studies, many of the studies are in this, because it is used in as a scaffold, as I told, or a drug delivery. So its antibacterial and antimicrobial properties are also well known. So now how this polymer can be used? It can be used as such in the field of water treatment, in the form of the beads, in the form of hydrogels, or it can be composed with some other polymers. like some other biopolymer, or imparting it a more properties so that the chelation property can be enhanced. And currently this has been also, nanoparticles are trapped into it to form the nanocomposites, which can also have a further enhanced activity in a solid form, so that the removal cleaning become easier. And then it is also used as imprinting, where the selective detection of or selective uptake of the compounds, desired compound can be taken. And the much of work is as interpenetrating networks, that is a cross-linked polymer, maybe as a semi-IPN or IPN. So this cross-linking, it imparted the property of getting the setting. And also the pores are created. The pores, they absorbent different pollutants, they can also be taken up, or it can simply take up the water. So all these are the various properties, and in various ways the chitosan has been explored. So for my work, it's as a eco-friendly sensing platform. The properties which are of interest, one is it's a multifunctional material, so we can play with all those properties, and that's what I have written, amenable functional group. Then this can be an alternative to synthetic sensory material. This can be the base material for developing the senses, and already explained natural film forming tendency it has. And furthermore, it has a water solubility, and depending, it can be again incorporating the hydrophobic groups or hydrophilic group, it can be amended. And relatively easily processing, and it is a chemosensitivity that I will talk later on. And there is a possible of detection of the hazardous material with this polymer. And moreover, being a biopolymer base, it is environmentally friendly, and a non-toxic probe can be developed from it. Now, as I am talking about the fluorescence sensing, so for a student, a word of fluorescence. So fluorescence, all of you know a process of absorption of light, with absorption of light excitation, then emission of light at a longer wavelength. So with this, we can have a platform whereby either we can monitor the intensity of light as a fluorescent turn-on off probe, or there can be shift in the wavelength. So it can be done in terms of ratiometric sensor, and then chitosan or the other polymeric materials, they can be explored as a sensory base material only, or after the modification. So here in this work, I will be discussing in brief some of the application as a fluorescence hydrogels, application of the chitosan, or chitosan embedded or capped nanoparticles which can be made to fluorescence, and or the chitosan itself is a functionalized, or it can be having a oligomerization. I will focusing more on that part. Or it can be simply a sensory matrix as a base matrix where the other fluoropores can be tagged. So these some of the things I will be describing over here. The first, the first report, it is where we are focusing on the primary amine group. Once we have a amine group, any aldehyde, okay, we are looking for the fluorescence sensors, fluorescence material, so we will look for the aromatic aldehyde, which can be simply from the ship base with the amine group. So, and then chitosan itself, it can polymerize to make a self-assembly of chitosan to form a hydrogel. So this hydrogel, once it is there, it is found to be, once the fluoropore has been added to that through amine group, it has been found to be selected for the Fe2 plus as a sensor. So both the properties are there as a hydrogel, gel to sol formation, or simply quenching of the fluorescence intensity. So on the upper side of I have shown that this chitosan itself self-assembled to form the cross-linked sol, and with the concentration of iron there can be change of the gel to sol solution, or it can be simply we are measuring the fluorescence intensity. So this work, it suggests that many of the aromatic aldehydes can be tapped onto this chitosan through the amine linkage, and then doing its photophysical properties, we can use them as a sensor. Though this is the work only potential of using as a sensor is reported. Now this work here where it has been used as a sensing of 2,4,6 trinitrophenol, again tagging the simple molecule like isocyanate, selectivity can be introduced for the 2,4,6 trinitrophenol. And similarly, a simpler, fluorophore, adding another polymer PVA, a gel can be created which can be again make a sensitive for the iron detection. So here I am going to, this is the work which is reported in the literature, and this particular work I will be explaining to you in a form of story, because most of the students are here. I just wish that the students, they should learn how small things, they motivate them to do something, and how and what way they can proceed. Even with the unknown, some things sometimes come in their research. So along with this, I will be elaborating all these things. Now here we have again focused on the amine group, converting this amine into simple basic reaction diazotization.
5 minutes.
So I have to then go fast with the nitrous acid. And now you will find the end product. It give a different fluorescence in the UV light as well as in a visible light. So, and then we use it as a sensor probing for the aluminium ion. Aluminium ion, it is otherwise, it doesn't come under the toxic heavy metals, but you know many of the water intensive industries, if the aluminium is present, for example, in the lead acid battery, if the aluminium is present, it will impair with the battery life. That's why its detection, quantification in the water is important. So I will be just going more and skipping some of the part. Then what's important is that out of many of the metal ion, how it comes with the, it pick only aluminium ion. So there comes your envision into the work that how come this process comes. So that's interesting for anyone who is doing research. Then you look for, when I look for its Mardi top, we find that it is no more a polymer. It has been broken into oligomer, and that oligomer, many studies have been done, it has entrapped this aluminium ion, and entrapping is possible only with the aluminium ion. So that's the way this has been developed. So I'm coming this as I'm saying, I am going to, can you give me just 2-3 minutes more?
Yes, please go
Okay. So KMNO4, once it is a COVID time, I stuck in UK, and there somebody called me that everyone is panic, what I should put in the water in my tank so that I will be free from the COVID. I said, just put KMNO4 into it, a small amount of it. And then he said, what is that? मैंने कहा आप जो लाल था वो वेल में डालते थे वो डाल दो थोड़ा सा. Or then I also searched why the KMNO4 as the oxidizing agent for water treatment has been stopped. And I come across that in the industry, pre-treatment step, still it is used. So then the only thing I find is that because of the aesthetic sense, it has been stopped. It is quite cost effective, but only the little bit pink color left, that's why it has been phased out for the water treatment. So I just think of working with this, and I find that out of this, with the KMNO4, though it is a pink in color, it get a bright red color. And the most interesting part, only journey I wish to share with the student, then my student come with that, with every change in concentration of KMNO4, she get a different color. As a chemist, I said, this is not possible. And 50 times she repeated the experiment, and the same results are coming. So our sensor, for a concentration, naked sensor, for a concentration is a remarkable work. And then we filed a patent for this work. But what's important, I want to talk to the student is that even your teachers say, no, this is not possible. Then you can repeat it that if the things are coming, if something unique is coming, then you search for that. And there we started with this as a concentration specific sensor. Then obviously I have to answer for publication, how does it comes? How is it possible? Then we go for all the detailed studies, and ultimately what comes out is, that's an interesting part, we have to go for authenticated that KMnO4 is an oxidizing agent. And mostly it changes from Mn7 plus to Mn2 plus. But the last one. And this particular oligomer, it just wrap around it and slow down the release of the electron. And instead of manganese 2 plus, it stops somewhere at a manganese 4 plus. So that gives a color. And different concentration of manganese 4 plus, it is a different color. So in that way, then we published this paper in Analyst and patenters in the grant stage. So then, as the time is there, I will not be talk much about. This is all already the chitosan capped, any of the zinc sulfide quantum dot or nano particles can be tapped into this. So that's my conclusion for the fluorescent probe that can be developed, which can be biocompatible, biodegradable. This is my own work also reflecting, where I am going for the optical sensor based on this. But this needs, I mean, as a scientist, as a chemist, I will say that it needs, ultimately to a sensory work with the physics, electronics, all people, they should come in hand to hand so that the lab research can go to the industrial or particularly societal application. With these words, I'm going to stop it. So again, a last message only for the students. Whenever there is a tedious process or talk, take it as a challenge. It's a new beginning always. So once and always start learning, reading, and whatever way you do, want study through phone or words. But if you stop it, it's like a person is died. So Albert Einstein is very dear to me. So it's always a new beginning. Thank you.
Thank you.
Thank you very much.
Maybe one question.
Yeah. It's a, this material is yes, we did with the stability. We did some of the study with the stability, and second is the sensitivity is highly sensitive, and we are moving, looking for this, developing as a optical sensor, a device. But yes, some of the things like stability operation over a longer period of time that we have to check, but thermal analysis, it shows it's quite stable material.
Okay, let's thanks to the speaker. And I think if you have more questions, she is here, you can ask. Otherwise, you can ask through the email.
Through email, because right now I will be leaving.
I understand you have a lot of questions. You must ask through the email.
Yes. Okay.
Thank you very much.
Thank you.
Okay. I would now request Professor Heather to felicitate Dr. Dheeraj Sood with a memento.
Okay. Oh, nice. Very good presentation. Maybe we will meet in the future somewhere.
Yeah, sure.
दे देना बिस्किट आपके पास
हाँ मुझे इंट्रोड्यूस करना है I think second invited talk by Dr. Bhanu Pratap. Let me introduce to Dr. Bhanu Pratap. He is here. Yes, in brief, of course, this is the new culture I am learning here. Otherwise, invited talk, we are giving more than 100,000. Nobody is introducing. Okay. Dr. Bhanu Pratap Singh is a senior principal scientist and deputy head at Advanced Carbon Products section of CSIR, National Physical Research Laboratory, New Delhi, India, and India, and professor at ACSIR. He obtained the doctorate from HT, Delhi, India. Dr. Singh research interest is on the large scale synthesis of carbon nano structures and their advanced nano composites for statistical application and anode materials for lithium ion batteries. Dr. Singh has published about 140 highly cited papers in a good journals, renowned journal. He has been awarded with the National Meritorious Innovations Award, CSIR Young Scientist Award in Engineering Sciences. With this brief word, I would like to invite to Dr. Pratap Singh.
Thank you, Chairman, for the introduction.
Okay, you have 25 minutes, and before 5 minutes, I will raise the hand.
Okay. So first of all, I would like to thank to the organizer for inviting me for giving a talk here. So topic of my talk is basically the carbon nanotube macro assemblies based multifunctional material. As we know, the carbon nanotube is a very fascinating material with an outstanding set of properties. The material having a different kind of a good properties, but carbon nanotube is a thing which is having its properties simultaneously, all the property in a single material. You can see it's have a high tensile strength of up to 150 GPa, modulus to 1 terapascal, good electrical conductivity, thermal conductivity, and the very light in the weight. And these can be produced by the different kind of a processing technique, as you know, the R discharge, chemical vapor deposition, laser ablation. Generally, when these carbon nanotubes are produced by this technique, it is in just like in powder form. When it is in powder form and you are going to make any kind of component or device, the property what I am talking about on the right side is the outstanding properties, but these properties are on the individual carbon nanotube. So to utilize this property in final component or product, it is very, very difficult. So that's why the reproducing this property at that macroscope level is still challenge in the present form. So the idea is when this carbon nanotube is produced in the powder form, if you are able to make some kind of micro assemblies, then the property can be translated in a better way as compared to the powder form. So this powder can be converted into the bucky paper by using this powder, but there another form of macro assembly is the CNT yarn, CNT sheets. So the macro scale form of CNT or CNT array, you can say CNT yarn, CNT sheet, CNT ribbon, bucky paper, and in all these three techniques, as I talked about the synthesis, the chemical vapor deposition is very much common, which is used for the large scale production. So when you are using the powder, this is substrate based CVD is used. And when you are going to make some kind of macro assembly, then FCCVD, the floating catalyst chemical vapor deposition is used. So this is basically how we are producing this carbon nanotube in the NPL also. We have a setup in which we can produce more than about 160 gram of carbon nanotube. But this carbon nanotube are able to make the macro assemblies. That means when you are making any kind of macro assembly, this having some high aspect ratio, the length should be in a better way. Then you can make it good type of a macro assembly, and with having a very good IG upon ID in respect to the multi-wall carbon nanotube with the more than 2 is very good number in terms of a large amount of powder. So by utilizing this carbon nanotube, a large number of studies we have carried out in the laboratories in the different kind of polymer system, with the thermoplastic and thermosetting. Thermoplastic, we did some studies on the phenolic and epoxy resin, and thermoplastic, the PMMA, polystyrene, LDP, ABS, polyamide, polyurethane, and polycarbonate. So with a different kind of processing technique, the solvent casting, twin screw extrusion, and injection molding. So what the property we studied, the mechanical property in terms of tensile strength, Young's modulus, bending strength, bending modulus, electrical conductivity, thermal stability, and the EMI shielding. So what we observed in these studies, the improvement in the electrical conductivity and EMI shielding has been observed, and very much dependent on the processing method. For example, if you're talking about the thermoplastic, two different polymer, one is polyurethane, another is a LDP. The both polymer have a different property in the initial stage. When you're incorporating only 1% of carbon nanotube, as in the LDP and the PU, the final numbers in both the polymer are very, very different. So you have to identify what kind of processing technique you are going to follow to make some kind of polymer nanocomposite. And the challenges which we observed in these studies with basically when you are loading the carbon nanotube in the slightly in the larger amount, in the agglomeration and dispersion and the limitation of the loading. The thing is, when you are adding any carbon nanotube into polymer system, that means you are not utilizing the property of the carbon nanotube. You are only modifying the property of the polymer because the limitation of the loading of the carbon nanotube. That's why you have to go for some kind of macro assembly in which a larger amount of this carbon nanotube can be incorporated in different systems. So for that, we were able to make a flexible CNT paper by using a technique in which we have a carbon nanotube, we disperse in some kind of DI water, and the homogenize on the higher speed. After there is sonication, and then the vacuum filtration will take place to make some kind of carbon nanotube. So these are setups which has been indigenously designed in the laboratory in which we can make a 35 centimeter by 35 centimeter of multi-wall carbon nanotube based CFD paper. And this paper basically has been tried for different kind of application. You see the ballistic application, anode material for lithium-ion battery, supercapacitor, photodetector, thermoelectrics, and lightning strike. So some of the application, how this macro assembly can be useful for this kind of application, I am going to discuss, in which the ballistic, lightning strike, or the structural, and the thermoelectrics. These are 4 components which I am going to discuss in a few slides. For the further modification of this property of the carbon nanotube paper, we are also trying to see what is basically the solvent which is used is basically DI water. So this is basically easily useful because of we are using the organic solvent, the cost and the treatment is also make a big difference. So when you are going to make a cost effective, the requirement is basically simply water, DI water. So DI water that have to disperse the carbon nanotube, then you need some kind of surfactant. So different kind of surfactant and the different ratios has been discussed with the 0.75, 0.6, 0.5 and 0.4. Then we found that the mechanical property with the ratio of the 0.5 was found a very good material. When we have to tailor between the mechanical as well as the electrical properties, then we can see that what kind of a surfactant will be useful for which kind of a properties. Then further, as I showed, for several application you need a different size of this carbon nanotube paper. Previously we have been able to make a 35 centimeter by 35 centimeter and we demonstrated for the anode material for lithium-ion battery. So then what happened, there's some kind of, when you're making some kind of cylindrical cells, then you need a roll of this carbon nanotube paper or separate length. So 35 centimeter is not sufficient, that you need around a 70 centimeter. So then you have to make some joint on that. So by making a joint on the carbon nanotube is very, very difficult. So then we established a new facility for that to making upscale this carbon nanotube paper from 35 centimeter to 1 meter of 1 meter. Then we can make a 70 centimeter bits of this tape, which can be very much useful for the anode material for lithium-ion batteries. Further, another application which I am going to talk about is structural composite. The structural composite generally used as a lightweight, high strength materials. And especially you can say nowadays in the aircraft industry or the high-end automobile sector, the carbon fiber-based polymer composites are people are trying. But there are some limitations to further improve the property of the carbon fiber-based polymer composites. So we explored some studies on that to utilize this carbon nanotube macro assembly in the terms of bucky paper. And what we did, we take a carbon nanotube and then we sandwich or interleave between the carbon fiber fabric layers. And then we make the sandwich composites which is having a carbon nanotube paper based hybrid structural composite. And then these are some kind of studies which has been carried out on the terms of the mechanical strength. You see the factual strength without interleaving with the carbon nanotube is 474, which goes to improve to 647, around more than 30% improvement in the by only adding the carbon nanotube paper in between the carbon fiber fabric. But another important point which we are going to discuss, this is basically electrical conductivity. When you talk about the carbon fiber-based polymer composites, it's a good to replace any kind of metallics, especially the steel. But you see, the steel having very high electrical conductivity. But carbon fiber having good electrical conductivity, but not as good the metal. And when they are using the sandwich composite basically the carbon fiber, and then there is epoxy. Epoxy is an insulating layer. So there are several number of layers, and there are insulating layer. So through plane electrical conductivity is not good. So that's why some kind of application where you are going to utilize this carbon fiber polymer composite, especially you can say when talking about the structural composite in aerospace. Nowadays the 50% of the weight of aircraft has been reduced by utilizing only the carbon fiber polymer composite in place of a metal. So there you need some kind of a lightning strike resistant material. So in the lightning strike resistant material you need some kind of copper foil on that. So copper having a higher density, so that's why we explore these materials you see for the lightning strike on the structural composite. See, there are 3 different kind of a composite material. In the 3 different composite material, the A1, B1 and C1. You see A, this is only the carbon fiber polymer composite, no carbon nanotube. And the B, the top layer is made of a carbon nanotubes. And C, there are 4 subsequent layers are basically sandwiched with the carbon nanotube paper. When C, then a very high current of 30 kiloampere was applied on that. You see the top figure, after 33 milliseconds, the burning of the polymer was taking place because of the through plane electrical conductivity due to the epoxy resin. Then when the only single layer of the carbon nanotube paper was attached on the surface, you see there is no burning. So that's why there is a great potential to utilize this kind of a macro assembly made of a carbon nanotube for using a lightning strike resistant material. The second application which we explored by using this carbon nanotube based composite material in the ballistic application. The ballistic, there are different kind of ballistic material, but the fiber based material generally use the Kevlar. We know the Kevlar and the Spectra, there are 2 polymers which are used for the ballistic material. But there is a problem of with the fiber-based armor, that is the delamination at a higher velocity. When you are impacting any bullet, the delamination takes place. Increased bear with the increased number of layers, slipping of fiber at high velocity, which reduce the performance, and the low strength to failure ratio reduce hitting capacity. So we did make the two different kind of a composite material. One with only the Kevlar tape by incorporating the carbon nanotube, and then the laminar composite. So in the first set of experiment, we disperse the carbon nanotube in the polymer matrix from different loading. This is a 0.05, 0.1, 0.2, 0.3 and 0.5. And then we found that only the 0.3% of carbon nanotube dispersed in the epoxy, showing the better result. So that results show that you can utilize the 0.3% of carbon nanotube in the epoxy. Beyond that, what is happening, the agglomeration again takes place. And we are using the carbon nanotube into the epoxy. What happens? Beyond the 0.3%, the viscosity of that epoxy increases very sharply. When you have higher velocity, then making the pre-preg or dispersing this carbon nanotube with higher loading very, very difficult. So incorporating beyond 0.3% is very, very challenging. That's why the mechanical properties start deteriorating. Then this is the basically all the tensile strength data for these tapes. We show that up to the tensile strength in Young's modulus of pristine Kevlar was the only 181 MPa and the 16.7 GPa. In case of 0.3 Kevlar epoxy, you found that the tensile strength was 350 MPa and the 16 GPa. What is exactly happening? You see that in a fabric, there are both direction. One is the warp direction and the web direction. So you can see the bridging of the carbon nanotube in the warp and web direction. Both directions taking place, which is improving their mechanical property in terms of their tensile strength. Further, there were limitation again. We say the 0.3%, beyond 0.3% we are not able to improve the mechanical property. Then what we did, we utilized the same carbon nanotube paper and then we sandwich between the Kevlar layer. So you have a 8 number of Kevlar layer and between them we interleave with the 7 layer of carbon nanotube paper. And the 4 set of samples are prepared. First is only the Kevlar. First is the Kevlar epoxy. Second is the Kevlar epoxy in which the epoxy, the 0.3% of CNT is dispersed. Another one is the bucky paper interleave, and fourth one is both the 0.3% of CNT as well as bucky paper interleave. So these set of experiments were performed, and then what we did, and then the mechanical property in terms of tensile strength and bending strength was studied. You see that tensile strength was improved by 55% of the final sample of KEBC in which both the carbon nanotube as well as the bucky paper was interleaved. And then similarly the bending strength was also in the 63% which was improved. So that's why showing a good potential to improving the mechanical properties by interleaving this carbon nanotube sheet or the paper in the Kevlar fabric. But this tensile strength and bending strength does not make any sense when you're talking about high velocity impact. That's why you need to do some other kind of testing which is called the impact testing in terms of ballistic property. So in the impact testing, what we have a drop tower test in which a weight of a certain height it comes and then contact to the of the composite material. So we did this kind of study and then we measured this energy absorption capacity. We see the dynamic impact was improved by 31%. In terms of by interleaving with the carbon nanotube paper, and then the static impact was also improved by 48%. So this shows that it's also absorbed more energy when you are interleaving with the carbon nanotube paper. And then this basically the visual inspection was carried out, which also showing the damage area. The damage area of the final sample KEBC having a lower damage area as compared to the without carbon nanotubes. Which showing that in case of KEBC the damage area has been reduced by 74%. So finally, then we tried with simply the bullet by utilizing the ballistic test of 3A. The 3A test which was carried out in the Gujarat Forensic Science University, where they have a facility in which what did, they have both kind of samples. One is the Kevlar epoxy, another is the KEBC sample. The 3 samples for each were tested and we see what happened in all the samples, the bullet was penetrated. But you can see the right side table, BFS, the backface signature. What is the backface signature? When any bullet is striking to the material, it's also damage your internal organ on that. So that's why there's a certain limit. This limit is there of backface signature. So, but we found that when you interleaving with the carbon nanotube paper, this BFS value is reduced by around 30%, from 126 to 27 to 88. That means the carbon nanotube is playing a role for absorption of the energy absorption of the in case of a bullet. So we found that, but the 8 numbers of layer was not sufficient to stop the bullet. So what we did, so then further studies, we tried to do some kind of study of the patterning of this Kevlar fabric. So with the patterning, there are different kind of patterning can take place, whether simply stacked, roll folded, or 3D interlock. So we take the Kevlar fabric is just like we we have this fabric made of a Kevlar, and then Kevlar fabric, you take a simple cut of the fabric and then sandwich it. Another is there is roll. You can make a roll and then you roll it. Another thing is you can make a 3D interlocking. When the energy absorption capacity of all these three were tested, we found that the 3D interlock is better option than compared to the simply stacked in terms of their energy. You can say 96, 111 and the 125. But taking into consideration, we also studied what happened when the drop tower test was taking place, the damage on that fabric. You can see the last one, the damage is less as compared to the top one. The fabric has been damaged in all the portion, but in the case of lower one, you can see the damage on the fabric is lesser. So that means energy absorption is better in case of a 3D interlock. By taking into consideration what we did, we take a 25 layers of Kevlar and it was rolled folded and the carbon nanotube paper was sandwiched between them and then the composite was played in the two form. One is Kevlar epoxy, another one is the Kevlar epoxy bucky paper sandwich. And then their ballistic test was performed in the similar way as in the previous test. In these cases, the bullet was not penetrated, you see. The bullet was stopped and then we see their backpack signature. You see the BFS of without carbon nanotube was 26, which has been reduced to 19. That means the carbon nanotube is playing an important role for stopping the bullet. So in that case, we found that it can be a very good option to reduce the number of layers of Kevlar for reducing the weight of the any kind of ballistic material. So further, the same sample was also struck with another set of bullets. So you can stop both the bullets, see, in the first bullet and the second bullet with the distance of 5 centimeters. So it shows that it's a pass, the level 3A test for the bullet testing by utilizing the carbon nanotube based Kevlar epoxy composite. So this was all about the one is the structural composite, then is the ballistic, and you see that another application which we just initiated in the laboratory for utilizing the flexible thermoelectric devices. You see thermoelectric devices, thermoelectric is basically to convert the waste heat into the electricity. We have a lot of waste heat, different places. But then the flexible thermoelectrics is basically used for the bearable devices. What do you mean by bearable devices? Just like a body heat. Our body having certain temperature and then the outer temperature different. So there is difference in the temperature that can produce the electricity as per the Seebeck rule. So we can see the carbon nanotube having a very good electrical conductivity. So that's why it can be explored in the form of bearable thermoelectric devices. So in the laboratory, we make this flexible thermoelectric device, you see, and the making the 60 pairs of P and N type, which was then this kind of showing the different temperature, the different power has been output has been shown. Up to the delta T, you can see this power density, and then it was explored in the thermoelectric devices. You can see the first top one. This device has been taken on the arm, and you see it's also generating some kind of a power of 4.27 millivolt, and then the delta T was only the 3 Kelvin. So, and then another is having to utilize for you can see the outside of the AC. That's also hot. You see the delta T was the 4 Kelvin. Another B part you can see, this is basically silencer. The silencer of the bike is basically hot. So this can be utilized for different kind of application in terms of bearable thermoelectric devices. And third, in the last part of this my talk is basically, whatever I talked about the carbon nanotube based material, just in the macro assemblies, which are basically the carbon nanotube we have powder and disperse into some kind of solvent and to make a filtration and make a carbon nanotube macro assembly. And carbon nanotube macro assembly, but when you talk about the mechanical properties, on the first slide I talk about is having high mechanical properties, but that was of individual carbon nanotube. Or you can say the carbon nanotube should be aligned in one direction, then this property can be exploited. But in this case, when you're making the carbon nanotube paper, this is basically carbon nanotube randomly oriented. So the property what I'm talking about is not realized in that carbon nanotube paper, but we can use in certain level. So in this case, the maximum tensile strength we found 8 MPa, but individual carbon nanotube high tensile strength. So you need to explore in certain other way. That's cast basically to make it some kind of carbon nanotube oriented. 2 minutes. Okay, this I will finish in 2 minutes. Another thing, the carbon nanotubes, oriented carbon nanotubes. So how to align this carbon nanotube? There are different way to align this carbon nanotube to make a carbon nanotube seeds. You can see the wet spinning, forest spinning, the aerosol spinning. So aerosol spinning is one of the technique by which we can make a large scale aligned carbon nanotube seeds. So we just established a facility in our laboratory by making the FCCVD. It's called floating catalyst chemical vapor deposition, in which we can make a sheet of long 20 centimeter width and 90 centimeter long. And you can see this is the process. So not going on, okay. So this is how the carbon pickers are coming out, and then it's basically cracked into the furnace, high temperature furnace, and that cracks going to as a, just like a soak and they're bounded onto the mandrel, and this showing the carbon nanotube in the better way in compared to the simply bucky paper. So this is a very good IG upon ID having a 5.7, and the sheet has been rounded onto the mandrel. And then this carbon nanotube sheet has been twisted to make a carbon nanotube fiber and also been demonstrated in different kind of applications, just like a conducting wire and fiber. You can say it's also taking some kind of a load. So the very small diameter can be utilized in the replacement of a copper wire. And then, okay, so I remove it, and then the last one, which the last part of this talk, this is what I'm talking about in the ballistic part. We are utilizing the carbon nanotube paper that also be able to absorb more energy as compared to without carbon nanotube. So then we are utilizing the FCCBD wet sheets that's showing the better performance as compared to the bucky paper. So in the 326 from 252, so that means in the reducing the number of layer only will be helpful for making the lightweight ballistic material in terms of using the carbon nanotube, aligned carbon nanotube sheets in place of bucky paper. So for that, we have also established a facility of larger size of that. So we can make a meter long carbon nanotube sheet in this way, and then can be utilized for making a lightweight ballistic material. Thank you very much. And this is an acknowledgement to all my students who are working on this different kind of projects. Yeah.
Thank you for the nice talk. One question, please. There is not much time. Yes, please.
How you have done this lighting study?
Yes. Basically, this we have a joint program with the University of Tokyo. That measurement was carried out in the Japan. What then they have a very facility on which they can apply 30 kA current on that this kind of a carbon fiber-based polymer composite. That has not been done in India. So plates have been prepared here, and then we send the sample there. So and then this is measured.
Did you check this carbon fiber composite that you have prepared laminates?
Sorry?
Laminates you have prepared with carbon fiber. So did you check the strength with this bidirectional by changing the orientation of the fiber?
That basically you can say the bending strength of this carbon fiber polymer composite, which was studied in the transverse direction. Okay, you can also measure in this direction, but basically when you talk about the carbon fiber,
you have arranged the fiber in one direction only,
no, this is a fabric, not one direction. It's a 2D fabric.
2D fabric you have arranged in like all the fibers in one direction, like one plane.
Carbon fiber are in the two planes. One set of 50% carbon fiber in this direction, 50% carbon fiber in this direction.
Saying like angle. Did you change the angle like 45-degree angle or 90
No. All the fiber in this direction, 50% fiber in this direction. The composite has been formed. Now you apply the load in this direction. So applying the load in the 90 degree of that existing carbon fiber.
Okay, detailed discussion can be done during the lunchtime. Okay, let's thank to the speaker for the nice presentation. And where is the girl? Yes, please come. Upar.
Yes, sir. So we would like to felicitate our Professor Bhanu Pratap Singh, sir. Please.
Yes. Okay, thank you very much.
Thank you so much, sir. Thank you for such an informative and interesting session, sir. I'm sure it will be beneficial for all our listeners. Yes, sir?
Left, no?
Yes, sir. So we would now like to invite our delegates for oral presentation. I'm sure everybody is present here for oral presentation. There are 3 delegates. And dear delegates, please note that the time limit for presentation is time constrained, 5 minutes only, and 1 minute for question and answer. So, and also for our evaluators, I would like them to be please come on dais. Dr. Bhanu Pratap Singh, Dr. Sashi Chawla, Dr. Rohit Verma. So our first presenter is Dr. Rupesh Basniwal. If he's here, yes.
Good afternoon to all. First, before starting my presentation, I want to thank organizing committee members for providing this opportunity. So my research is microbial detection with chemically modified nanoparticles. The problem statement is that if you see loss of water contamination is due to different microbial pathogens. So is there a possibility that we can detect it? Yes, we can detect it, but if you see, detection is very, you can understand, the detection is very time-taking process, and it requires at least 24 hours, means almost 1 day. So if you see the existing methods which are available, like serial dilutions, and further, we have a fast alarm kit which is going to detect almost after 24 hours. So the point is that can we detect it fast? Yes, we can detect it with the help of nanoparticles. Nanoparticles which are going to functionalize with a specific technique that can be used for the detection of microbial organisms. So if you see, we can detect special analytes with the special type of functional groups which is going to attach nanoparticles. So you can see we can detect it E. coli with the help of functionalized cysteine on gold nanoparticle, and we can detect arsenic with the help of functionalized with polyethylene glycol on gold nanoparticle. So like that, many analytes are there, we can detect it. So here we have opted this methodology for the detection of this E. coli in contaminated water. So first we have to select the material, then we have to see its performance based on their pH, temperature, time and concentration. Then we have to go for interfering agent study, and then finally we are going to design a prototype, and then we have to move towards a field trial. So this is the culture we have received from Jamia Islamia University in form of agar saline. Then we have cultured it in broth medium, which is means nutrient agar, means agar is absent in this broth medium. Then further we are going to incubate at 300 RPM at 37 degrees centigrade for 24 hours. Then after the incubation we can see organisms on this agar plate culture. So this is the basically synthesis and functionalization of gold nanoparticle process. This is the conventional Turkevich method you already know. And further we are going to functionalize this gold nanoparticle with the help of cysteine molecules, and we have to keep gold nanoparticle and cysteine at 1:1 ratio. So after the functionalization, we are going to move towards characterization. So here we can see this is the this is the spectrophotometer graph for the gold nanoparticle, and after the functionalization with the cysteine, you can see there is a slight change in their absorption reading, means it's going to shift almost 10 to 20 nanometer towards the higher wavelength. And when we are going to further add the E. coli microorganism, then you can see the patterns is going to change. If to analyze this, then we further move towards scanning electron microscopy. So you can see we have analyzed gold nanoparticle with the help of scanning electron microscopy, and further the functionalization done by the cysteine molecule. We can see it with the help of this cell image. And this is the image of E. coli bacteria, and this is the images of the bacteria after the interaction with gold nanoparticle. So further how we are going to detect it, you can see here. Just if we are going to take only distilled water and we are going to add in control gold nanoparticle which is already functionalized, that it is not going to show any color change. But when we are going to add contaminated water, then it is going to show the color change. So this is the basic thing which we have to opted for this study. Further, we can see that if you are going to spike the E. coli directly, then it's also going to show the color change. And if you are going to take a RO water, then it is not showing any color change. So it is clearly indicating if there is E. coli present in the contaminated water, then it's going to show the color change. So here, further we have moved towards the device fabrication. So you can see here, this is the control cysteine functionalized gold nanoparticle solutions, and when we are going to add contaminated water, then it's going to show color change. So this color can be further studied with the help of this our fabricated device. It will be going to show some particular reading, and that reading is going to corresponding to particular absorbance, right? Like as conventionally we do in our spectrophotometers. Then further interference studies is also done with different metals, and there is no interference observed in this case, and these are the optimum conditions for the E. coli interaction with the nanoparticles. So, and this is the final image, or you can say real image of our device, and this is the schematic layout of the device, and further we have to do we have to detect heavy metals as well as organisms simultaneously, and this is the output from this work in form of patent. And finally, I acknowledge the financial aid we have received from Department of Science and Technology, Government of India, and this is our research team member, and Dr. V.K. Jain is our mentor and guide, and you can see here Dr. Devendra Madwal, who has contributed in this for making a device, and rest of them researchers are also involved. Thank you. So if you have any question, you can ask. Yes. 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 Actually, if you see, the cysteine affinity towards E. coli is very high, and it is going to electrostatically bind with the E. coli microorganisms. That's why I have choose it. Yes, yes, yes. Yes, yeah, if you see in this, I already shown in my slide. So basically we are using this EDC NHS chemistry for the functionalization. Haji? No. First we have to add the carboxylic group on the gold nanoparticle, and then further we have to interact with cysteine molecules, which is going to make a cross linking. So any more question? Size of nanoparticle. Yeah. So size of nanoparticle is going to vary. If you are going to see the image of our SEM, you can see here. So size of nanoparticle means it will be more than 200 nanometer. Means around 350 nanometer. We have already checked it. Yes, I think we are getting late. So thank you.
So our next presenter is Garima Nagpal from Sharda University.
Good afternoon, all of you. My topic is nanomaterials for bacterial sensing, current trends and future prospects. Basically, there are various types of pathogens, including bacteria, virus, fungi, and protozoa, and they all are belonging to the kingdom Eubacteria, and maximum of them are the pathogenic in nature. They are mostly creating contamination, and they are causing serious threats to human health and safety. And approximately 1/3 of all fatalities worldwide are attributed to bacterial food poisoning. The World Health Organization predicts that throughout the next 1 or 2 decades, the ability to present antibiotic to combat disease will decline. So there is need that these bacteria should be sensed early in the stages. Although some technologies are already available like PCR and ELISA, but the problem is more time consuming. And so there is need that there will be development of some biosensors which will detect these bacteria at the early stage and will lead to the detection. So nanomaterials can enhance the performance of biosensors as they have large surface area which allow for efficient capture of analytes. Magnetic nanoparticles, gold nanoparticles, silver nanoparticles, and quantum dots are examples of nanotechnology-based methods that demonstrate selective target binding properties. They are the best option for the biosensing and detection of bacterial illness because of their qualities. Basically, how these nanomaterials basically work as in a biosensor. In a biosensor, basically, there is a recognition element. This recognition element can be an antibody, aptamer, phase, or electrostatic interaction. These recognition elements, they bind with the target analyte, and then there must be a transducer which will translate this binding event into the signal, and these signals are detected in the form of biosensors. And compared to normal materials, nanomaterials have distinct mechanical, optical, magnetic, electrical, and physical properties. They are very tiny size and large surface area improve its sensing capabilities, and there are various nanomaterials which are used by researchers to improve biosensing findings, accuracy, sensitivity, and shell life. So basically, there are a wide range of potential uses exist for biosensor in agricultural production, environmental monitoring, including online infield and real-time detection of antibiotics, microbes, toxic materials, pathogens, pesticides, proteins, odor-causing bacteria, etc. in water, air, animal, food, soil, plant, and food processing also. Basically, they detect they combine these biosensors, they combine with bacteria and viruses, and they react with their protein, enzymes, antigens, and DNA and cells, and they result in some change in the properties of the nanomaterials, like optical, electrochemical, or any other property, and in the form of transducer, they produce the signals. A change in the refractive index of antibody conjugated nanomaterial cause a shift in the absorbance spectrum peaks, and thus indicating the presence of target bacterial cells. Biosensors may find use in the following areas like bacterial sensing, water analysis, farming, healthcare, water treatment, and agriculture. So basically, what is the mechanism of bacterial sensing using nanomaterials? First, there is induction of intracellular effects such as interaction with DNA and protein. Then there are reactive oxygen species production, which indicates there is a reaction of the nanomaterial with the microorganisms. And then it leads to the disruption of the cell wall of bacteria and reduction of the development of biofilms. Then there are recent advances in nanomaterials for bacterial sensing. Nanomaterials are being used in commercial goods at a very fast rate. Surface water resources that are contaminated with waterborne pathogens pose a serious hazard to human health and life on a global scale. Recently, biosensors have been considered as appealing substitute for the traditional pathogen detecting platforms that are now in use. Biosensors are devices that are intended to identify and measure different biological substances like certain DNA sequences, proteins, oligonucleotides, viruses, and bacteria. But there are some challenges as well as limitations for the use of biosensors. These challenges include sensitivity and specificity, biocompatibility, stability, and longevity. And their limitation also include that they also may exhibit toxicity, and biocompatibility may vary depending on the type and concentration of the material. Then nanomaterials offer significant potential for bacterial sensing applications, providing unique properties that can be harnessed for the development of sensitive and selective sensors. However, several challenges and limitations need to be addressed to fully realize the practical application of nanomaterial in this field. Efforts are going on to enhance the sensitivity and specificity of nanomaterial-based sensors, ensuring accurate and reliable detecting of bacterial species or strains, and the cost associated with the production and integration of these sensors, as well as the need for regulatory approval, are important factors influencing their adaptation in real-world systems. Addressing these issues will be crucial for making nanomaterial-based bacterial sensors more accessible, especially in resource-limited environments. Thank you.
So our last presenter for today is Monica Srivastav from Sharda University.
A very good afternoon, all of you. I'm Dr. Monica Srivastav from Sharda University. The topic of my presentation is impact of whole transport materials on perovskite solar cells. So the contents will include the introduction, experimental techniques, result discussion, outcome, conclusion, and references. So first of all, we should know that what is a solar cell. It is a photovoltaic device that converts the light into electrical energy based on the principle of photovoltaic effect, which says that light as it enters the photovoltaic cell, it imparts enough energy to some electrons to free them. A built-in potential barrier in the cell acts on these electrons to produce a voltage which can be used to drive a current through the circuit. So there have been 3 generations of solar cells. The current work is based on basically the perovskite solar cells, which are of low cost, but they are highly efficient. So this is the NREL chart, which shows that within a very short span of 10 years, the maximum efficiency which is reached by the solar cell, by the perovskite solar cell, is 26.8%. So this is the perovskite material, which is having the general formula of AbX3, where A will be methyl ammonium ion, B will be lead ion, and X will be the halide ion. Here we have taken iodide. And so the perovskite material which will be used in the research process will be methyl ammonium lead iodide. So it has some remarkable properties. It is first of all solution processed. It has high absorption coefficient, high diffusion length, high charge carrier mobility, and a low exciton binding energy. It has very important tunable band gap, and of course the efficiency which it has reached within a very short span of 26.8%. So this is the basic mechanism which will be followed in the present research work. This is the sandwich structure perovskite cell we are talking about. Here we will have a working electrode, a counter electrode. On the working electrode we have a layer of blocking layer and TiO2, that is the electron transport layer. Then our sensitizer material, which is followed by HTM. Now to provide a better contact between the HTM and the counter electrode, we are taking a polymer electrolyte, PEO based polymer electrolyte. So in the synthesis process, we have the preparation of methyl ammonium iodide, which is done by the ice-bathed treatment. And we are using 3 HTMs, that is the whole transport material. 2 of them are inorganic, that is copper iodide and nickel oxide. And one is the organic HTM we are using, that is P.PSS. So first of all, the process is followed as the preparation of working and counter electrode, synthesis of the perovskite. The perovskite solution is coated on the working electrode. F-2 is kept on the hot plates at 70 degree. HTM is spin coated on the perovskite layer, and then the polymer electrolyte is drop casted or spread over the HTM layer to provide a better interface and of course acting as the redox couple. So when we are preparing the working electrode, we are basically using F-2, that is fluorine doped tin oxide conducting glass plate, which is coated with the blocking layer, and TiO2, that is the electron transport layer. It is being used by the Dr. Blade method, which is sintered at 500 degrees Celsius. Counter electrode, we are using H2PtCl6 solution over the F-2, and then we sinter it again at 500 for 30 minutes. The standard PEO-PEG KiI2 polymer electrolyte is used here for the better contact. So this is the characterization which has been done on the perovskite material. It is showing the optical activity. So here, first of all, the sample has been observed under daylight, which shows a yellow color. But when the same solution is observed under UV light at shorter wavelength of 254 nanometer, it emits green color radiation. Then there is SEM analysis, which is showing the rod-like structure of the perovskite material. The EDAC shows that all the components are present while the synthesis, and X-ray diffraction analysis is following the literature through the JCPDS data. This is the atomic force microscopy, which is showing that the layers of TiO2 and perovskite put over here, when only TiO2 is there over the F-2, the reference is 13.9, and when the perovskite is coated over it, the roughness is reduced to 10.7, which shows that there is a proper spin coating of perovskite over the surface. Then there is, we are using nickel oxide, so the SEM analysis shows the different magnification of nickel oxide. EDX shows the formation of nickel oxide. And in this case, we are having a maximum efficiency of 10.03%. We are having another HTM, that is copper iodide. With that, we are having an efficiency of 13.64. But the maximum efficiency we are getting with the organic HTM, that is P.PSS. And in that case, the maximum efficiency which has been reached is 15.24%. So the stability which has been repeated, that is for P.PSS, we are getting a maximum stability of 17 hours. And for inorganic HTM, we are getting a maximum stability for 2 hours and 2.5 hours respectively. So the basic issue with the perovskite solar cell is that the use of lead. So now the future work is basically based on removal of lead from the perovskite. We can use germanium, we can use bismuth. So this work is being continued in the further process. Thank you very much. Yes, sir.
How do we confirm from the index NiO of form, nickel oxide?
So the composition, elemental composition. Yes, sir. So we are having an impurity of carbon.
Which stage of Ni or oxygen has been prepared? Can you say how can you confirm from the index?
So we have prepared the sample on the F-2 and then given for the characterization process.
उसके अंदर निकल भी है ऑक्साइड और ऑक्सीजन भी है तो
Sir, the nickel oxide has been prepared by the sol-gel method in the powdered form. Then it is being coated on the F-2 and then we have. Okay, thank you.
Thank you, evaluators, and thank you all for being so patient with this. So we can continue for the lunch, and after lunch, I request you all gather for technical session 5 here. Thank you.
Environment and Sustainability Institute, University of Exeter, UK, and Dr. Aurangzeb Khurram Hafiz, Jamia Millia Islamia, to please come on the dais. We are honored to have with us Dr. Bhanu Pratap Singh as our session chair. It is my privilege to introduce Dr. Bhanu Pratap Singh. Dr. Bhanu Pratap Singh is a senior principal scientist and deputy head at Advanced Carbon Products section of CSIR National Physical Laboratory, New Delhi, and professor at ACSIR. He obtained his BTech from Institute of Engineering and Technology, Lucknow, and MTech in Chemical Engineering from IIT Kanpur. He obtained his PhD degree from IIT Delhi. After completing MTech, he joined CSIR NPL as Scientist B in 2004. Dr. Singh's research interest is on large-scale synthesis of carbon nanostructures and their advanced nanocomposites for structural applications, anode material for lithium-ion batteries, efficient EMI shielding material, and lightweight body armor materials. He has created a facility for large-scale synthesis of MWCNTs using CVD and developed variety of their composites of significant improved physical and chemical properties. He has also made significant contributions in the product development based on CNTs. 3 NOS of the US patents of CNT-based material have been granted. He has supervised 4 PhD students and currently supervising 8 students. Dr. Singh has published more than 140 highly cited research articles in high impact factor journals. He also published 2 books and 14 chapters in books. He has been awarded for various prestigious awards like NRDC National Meritorious Innovation Award, CSIR Young Scientist Award 2015 in Engineering Sciences, IEI Young Engineering Award 2017 and HEAM Young Scientist 2014 Award by Indian Association of Hydrogen, Energy and Advanced Materials in 2014 and several Best Paper and Poster Awards. We welcome you, sir.
Thank you.
I now request Dr. Bhanu Pratap Singh to kindly introduce our keynote and invited guests to deliver their talks.
Thank you for the introduction. Now we are going to start post-lunch session in which we have one keynote speaker and 3 invited speakers. So first, I would like to introduce our keynote speaker, Dr. Vinod Kumar. Dr. Vinod Kumar is the assistant professor, JNU. Dr. Vinod Kumar did his bachelor's and master's from Delhi University and PhD in material chemistry, also from the University of Delhi. He has over 15 years of experience and is currently working as assistant professor at a Special Center for Nanoscience, JNU. Dr. Kumar has successfully completed various research projects funded by SERB and UGC. He has also been awarded with SRF by CSIR and JRF by UGC. He has various research publications and international and national journal and proceedings. So now I invite Dr. Vinod Kumar, please deliver a talk.
Thank you.
Oh, we can sit there also.
अच्छा वहाँ पे आएगा इसमें हमने पीपीटी डेस्कटॉप पे सेव की थी अच्छा प्लीज ओपन इट Thank you, Professor Bhanu Pratap, for nice introduction, and I also thanks the organizing committee members for giving me the opportunity to present my research work. And before proceeding, we must know the government of India, not government of India, all the governments throughout the world are focusing on the hydrogen economy. And when we are discussing the hydrogen economy, as we see this one, hydrogen generation could become a $1 trillion market per annum in near future, and still it's which we see in 2022, it is $126 billion. It means there is a huge scope in hydrogen economy. And somehow if we do some startup and so many things in hydrogen economy, then it's a really great work for the nation, and it can lead to the entrepreneurship for the young mind. And on these things, now I would like to start my lecture, that this work is based on the engineered SNO2 nanoparticles and their activity for hydrogen generation. Now my current research area, if we see, wastewater treatment, where we are dealing pesticide, pharmaceuticals and other contaminants like dyes, heavy metals, and other one is electrode materials for lithium-ion batteries, and one is waste management, where we are converting plastic waste into value-added products. And this session I would like to tell about the hydrogen generation. Why hydrogen generation is so important, and why I have chosen metal oxide nanoparticles, why there is a necessity of engineering their band gap, and so on. Now, why do we need energy? If we know the SDG 7, Sustainable Development Goals,
we know energy is a very important parameter. And if you see data 2010 with the latest one released by WHO, so 1.2 billion people without access of electricity in 2010. But now the population 259 million people are still without electricity. If you see, there is a decrease in number, but if you know, there is a huge growth in population also. And after 12 years, still lot of people are lacking the electricity. Means it is a huge demand throughout the world. Then 3 billion, if you see 2010, 3 billion people without access to clean cooking. Yani food is another problem. Then total energy, even light, and you see the market rate. It means there is a huge demand of energy in this scenario, because everything, if you see, all are made of some gadgets which require directly or indirectly some electricity. Whether this pointer also, we need a cell in this one, laptop, printer, lights, and everywhere. It means in near future, if we can't focus on the energy, it may cause a lot of problem, scarcity throughout the world. So the major challenge is increasing population and depletion of fossil fuel. Means we have to move the renewable sources of energy, wind, sun, and others. Now, how to overcome this energy crisis? Do we have a caller mic? कॉलर माइक है हमारे पास, अब वो दे दीजिए ना, फिर ऐसे
हेलो
पीछे की आवाज ऑडिबल होनी चाहिए, नहीं वो सही है। Thank you so much. Now, if you see, if we know that sun, it generates huge amount of energy, and even we can't utilize 1% of the total energy released by the sun. If we want to fulfill the energy consumption criteria for humans, at least 10,000 solar plants we needed, 10,000 throughout the world, with very high energy generation. And that is, in current scenario, I don't think it is feasible. And for next 10 years, that is also not feasible. Means we have to use different types of energies so that we can fulfill the energy requirement. Like for example, the government now adding ethanol in petroleum. It reaches to 10% blending. Now in future, it will reach to 20%. And because of that, last year, the government saved approximately 40,000 crore plus carbon footprints. Yani we are releasing less carbon in the nature. So ethanol blending, and there are other several types of energy formation are there. Now my aim to form the development of hydrogen economy, and especially on the basis of solar energy. Now solar energy based water splitting, if you see, there are several ways to generate dihydrogen. One is thermochemical water splitting, where we are using high energy like 400, 500 degrees Celsius temperature. Then photobiological water splitting, where we need enzymes, but enzymes, the efficiency of hydrogen are very, very less. Then photoelectro water splitting means we need electricity. So our aim that to choose some cost effective method, that is photocatalytic water splitting, where we are using catalyst and we are suspended in the water and we are split the water in H2 and O2 with the help of sunlight. Now this is the mechanism. If we see conduction band and valence band, they play a very important role for the generation of dihydrogen gas. Now if we talk about the valence band, if we want to generate oxygen, then valence band must be more positive than 1.23 volt, and if we want to generate dihydrogen gas, then conduction band must be more negative than 0. So somehow if we reach that conduction band more negative to 0, we can generate dihydrogen gas. So that's why this is the NHE diagram for hydrogen generation of various metal, oxides, selenides and other materials. So if you see that silicon carbide, TiO2, ZnO, CDS, gallium arsenide, cadmium selenide, these are some of the materials which has been utilizing for the hydrogen generation. But there is certain problem like energy absorbance, recyclization, photocorrosion and so many things. And if you see that SNO2, its band gap lie below the 0, means more positive. That pure SNO2 is not sufficient to generate dihydrogen, as its band gap lies below 0. Means somehow if we manage to engineer the band gap of SNO2, it will reach to more negative, then we can generate dihydrogen gas. And this is our aim, ki how to increase the band gap of SNO2, means how to move the conduction band to more negative, not increase the band gap. So this is already I have told you. Now why I have chosen SNO2? That we all know TiO2 is a very well known photocatalyst, and from last 50 years hundreds of scientists, thousands of scientists are working, and each year we have huge amount of publication for TiO2. If you see this one, 5,000, 4,000, 3,000 each year, and till date we unable to get any breakthrough from bench to market. And this data has been recently published in Chemical Engineering Journal, and we have also compared with SNO2. If you see, if with respect to photocatalyst and hydrogen generation, SNO2 is very less explored with respect to TiO2. So this is our aim, to choose SNO2 over TiO2. Now if somehow we can make SNO2 for hydrogen generation, so we can modify the SNO2 with other materials to have more hydrogen efficiency. So this is our aim, to choose SNO2. Now band gap engineering is another task. And why it is needed? For dihydrogen gas, we have to move the conduction band to more negative. This is first aim. Then widen light absorption range, improve morphology, redox potential, and the last and foremost, recombination rate. Whenever we are irradiating light over semiconductor, the electron from valence band jump to conduction band, but at the same time it combined with the hole. Yani recombination rate are very high for semiconductors. So our aim to minimize the recombination rate so that electrons are available for hydrogen generation. And that there are several ways that we can modify the conduction band of the nanomaterials or SNO2. And our aim, that doping. Through doping, we have changed the band potentials of the SNO2. And for this, and first structural aspect, before going that, it is a very beautiful rutile structure, SNO2, and where SN is sitting at the center and 6 oxygen is surrounded the SNO2, and SNO6 tetrahedra has been formed, And this is the various rotations, different rotations where we can see the crystal structure. And now when we are doping the things, so we can see there is a distortion in the structure. Means whenever we are introducing the other dopants, it distorts the structure, and due to distortion there is a generation of oxygen vacancies, and also the band position moves. And this is one of the theoretical studies, and looking this we move further. So here in this work we use 3 dopants: cation, anion and boron, which property, some of the property lies with the metal, so in between metal and non-metal semi-metal. These 3 dopants we have used for the changing the band potential of SNO2. Now the comparison between cerium, boron and nitrogen doped SNO2. If you see, the size of cerium ion is much larger than tin 4 plus ions. So means if more size replace the smaller size, so it again distorts the structure. If then charge imbalance, there is a charge imbalance, means there is a generation of vacancies, yani disorderness in the system. And boron, if we talk about the boron, the size is smaller than tin 4 plus, again it can cause disorderness in the system. When we talk about the nitride ion, the size of nitride ion is larger than oxide ion, O2 minus. So again it distorts the structure. Means that's why we have chosen cerium, boron and nitrogen. Now synthesis procedure is very simple. We have to take cerium on boron source, H3BO3 for boron, cerium chloride we have used for the dopant, and SnCl2 2H2O as a tin precursor we have used, and through reflection we have doped with cerium and boron. And for nitrogen we have used hydrogen for the nitrogen doping. And after successful synthesis, the categorization of these 3 material. And if you see the bands, it matches with the rutile structure, and JCPDS we have matched this one, all the data. And if you see the broadness refers the nanoparticle size. It is the preliminary study about the nanomaterial has been formed. And if you see, all are in nano size through this XRD parameter. Now we have also studied the Raman. Raman tells about the defects level, how much defects has been formed in your system. Now the band at 563 or nearly 550, it tells about the oxygen vacancies, yani defects in your SNO2. So if you see this, and we have also compared with pure SNO2. We have synthesized the SNO2 without any dopant. And if you see the comparison, there is a broadness in this band 563, means there is a great disorderness and oxygen vacancy has been created in the system. And similar for boron doped also. And for comparison we have not shown here because 2 places we have seen. So here also there is a huge band at 577, yani oxygen vacancy and disorderness has been created in SNO2. Now if you see the morphology and particle size, so through time we can see the particle has been nano range size, and whatever the agglomeration we have studied, because as the size decreases there is a van der Waals force of attraction increases, that's why there is a agglomeration with these nanoparticles. Now band gap, if you see this one, we are getting pure SNO2 3.71 and doped SNO2 3.80, means there is an increase in band gap we have observed when we are introducing cerium in SNO2, means this effect is known as Bose-Merstein effect. The Bose-Merstein effect is that whenever you have more charge carriers, it shifts the band potential to above. Means we are able to increase the band gap and conduction bands moves to more negative. And for similar boron doped SnO2 also and nitrogen doped SnO2. Since we have synthesized nitrogen doped SnO2 with different method, so we have not shown pure SnO2 here. Now XPS analysis. If you see through XPS, there are two different types of cerium, cerium 3 plus and cerium 4 plus. Both have been doped in SnO2. And when we are talking about the oxygen vacancies, the oxygen vacancies we can tell about the deconvoluting the oxygen peak which we are getting through core level O1s. And when we compare with the pure one we are getting only 2 bands, while in cerium doped SnO2 we are getting 3 bands. And the last band whatever we are observing, that is because of oxygen vacancies which has been created in SnO2. Similar for boron doped SnO2, the similar studies, and for nitrogen doped SnO2 we are getting only one type of oxygen. But the dissonance is also there in nitrogen doped SnO2. Now hydrogen evolution results. So we have also used different sacrificial reagents. And why we have introduced sacrificial agent? Sacrificial agents are those which have tendency to donate electrons or to capture holes which has been formed during radiation of light over semiconductor. Now we know that there is also chance of generation of dioxygen gas. So when we use sacrificial agent, it decreases the dioxygen gas by capturing the hole. If hole is not free, so the dioxygen gas is not released as much. So our main focus to generate more hydrogen and less dioxygen. So that's why several sacrificial agents we have used during our studies. Now here also if you see the pure SnO2, the hydrogen generation is very negligible. Means we are getting nothing, almost zero hydrogen. But whenever we are using our cerium doped SnO2, boron doped SnO2 and nitrogen doped SnO2, we are able to succeed generation of dihydrogen gas, and these studies we have done first time. Means doped SnO2 is not known for hydrogen generation. It's going to over soon. And this is the mechanism that we have already discussed, so there is no need. And this is another research area of mine, only 2 slides, where we also work on the water purification. So here we have developed the very strong absorbent for the removal of dyes. I think video. There is no codec file here, so I can't run the video. So within 1 minute it absorbs the dye over the surface, and this one also it will not work. So I will tell little bit about these 2 experiments. One is within 1 minute we are able to absorb the dyes over the nanoparticles. It means it is a very highly efficient nanoparticle for absorption of dyes. But problem is there, if you use the powder form, you can't separate powder from the water. There is always nanomaterials present in the water. Whether you use high centrifugation machine, anything, it's very tough to remove the nanoparticles from the water. Means for application part, we can't work with the nanopowder. But in the second video, now we have formed the beads of the nanoparticles, and it also removing the dyes all the N90 dyes. This is one of the dye. We have also done the mixture within 1 minute. And we have also patented this one, and we have filed the US patent for this part. And why this one is so important? Because nanotoxicity, because whenever we are discussing the nanoparticles, very good, glamorous. But the other aspect is nanotoxicity, which is highly dangerous. And I am sure after 10 to 20 years, we will discuss only about the nanotoxicity, like pesticide we are discussing. Pesticide is very carcinogenic and so and so. And after 10 or 12, 20 years, we will discuss the toxicity on the same university and throughout the world. So toxicity is another problem. Means if we are leaching of nanoparticles is another serious concern which stops the nanomaterials for the practical application for so many things. So we have to stop the leaching of nanomaterials. That's why we have used the beads. And that video I want to show, but since it is not playing, we are unable to play. Conclusion, and this is the very beautiful campus of JNU, and this is our nano center. As the name suggests, nano, so our center is also similar to nano, very simple. And these are our gems of my lab, and Bhavna and Sanjeev, they are working on the hydrogen generation. Shikha, he performed all the attachment we want to show. And then Rishi, Monica, Ritu, they working on the pesticide and pharmaceuticals. And these two recently joined, Karambir and Abhinmanyu. And they will work on their own. Let's see. And thank you so much for listening to me.
So you mentioned that we are not able to use like nanoparticle for the removal of these things. So when you're making a bead, you don't have anything like it can tear off some nanoparticle, because yesterday some speaker was saying about this nanocomposites, something of plastics is coming on with this wrapper, or that's very, very minute, and we are actually inhaling it. So are you sure that, when using these beads, it will not go into the water? Still,
yes. It's a very good question. And after this experiment, we have also done the ICP for the water that we have filtered out. And we have not centrifugation, we have not used any centrifugation machine. We have only simple filter out. Then ICP, the percentage of tin, because I have used tin material here. Okay. The percentage of tin is 7 BBP, yani parts per billion, ppb, sorry. So that concentration is acceptable and within the WHO limit. That we have also have some standard by WHO. So it is below par level.
So when you try to make a bead, then
yes.
it is some binding agent you are
yes,
using?
binding, you can say it is a binding agent.
It's a binding agent, you are using it with this
particle, and because it encapsulates the nanoparticle, and the nanoparticles are unable to remove, we are unable to remove the nanoparticles even after huge stirring, because whenever you are performing the result, that there is a huge stirring.
Yeah, it could be a little bit more curious.
Because that video we are unable to play, that's why I told you, can I use my laptop?
Still a little curiosity.
So now that there are so many techniques that those are available these days, we are reducing the leaching of nanoparticles for the practical or viable application.
Sir, what's methods to detect pesticide residues in our fruits and vegetables?
It's HPLC.
Oh,
simple. Because that if you talk about the vegetables, the amount of pesticide is very, very less. So through using simple UV visible spectrophotometer, you are unable to get the band. And if somehow you get the band, you are unable to tell whether it is due to vegetable. There is some organic materials also in vegetables. So,
have any portable machine just to see whether our vegetable is having a pesticide.
So only you have to do some MS technique, mass spectroscopy. So only that through we can tell. But you are preparing your own pesticide solution at lab, then it's easier that you can detect through UV visible spectrophotometer. But anyhow, you have to go for HRMS. What are the intermediates it has been formed if we are degrading the pesticide. So we must know the intermediates formed.
I think let's close here for the talk, and you can discuss later on, because we have to again complete another talks. So let's thanks Dr. Vinod Kumar for excellent talk. It's very important for the purification of water and using this kind of a catalyst material. Okay, thank you.
Thank you, sir. Thank you.
Now we have another talk. Dr. Anurag Rai.
और बताइए क्या हाल चाल है भाई तुम्हारे? अच्छा अच्छा भेजा था आपने.
A brief introduction of Dr. Roy. Did his bachelor's in chemistry from University of Kolkata, master in chemistry from IIT Dhanbad, and was a research associate at R&D Tata Steel, Jamshedpur. He did his PhD in chemistry from CSIR, CGCRI, Kolkata, and presently a postdoctoral researcher at University of Exeter. He has over 70 research publications in international and national journal and proceedings, and 4 published book chapters. He has been awarded with various awards internationally and nationally. He is expert in synthesis, structure property, performance correlation established by DSSC, perovskite solar cells, polymer solar cells, solar thermal materials, and smart material development for window glazing, building integrated photovoltaics, facade and passive cooling application. So now I invite Dr. Roy, please give a talk. We have 25 minutes. Yes? Okay.
Thank you, Professor Singh, for your nice introduction, and good afternoon, everyone. My name is Anurag. I'm Indian by looking, but currently I work for the University of Exeter, which is in the southwest of the UK, England. I live in the UK in last 7 years, and obviously now I'm half nationality over there. Anyway, today we are here gathered for the unrevealing some interesting new trends of materials, devices, and I'm going to take you, all of you, a journey of the recent trends, materials of solar energy research. Solar energy, which is not only of photovoltaics, but at the same time, there are another way of generating energy utilizing sun, which is free of all. So let's see our group, which is working on the solar energy materials and devices, and we are from the Renewable Engineering Department in the Exeter University. So hopefully you will enjoy today's talk. And before moving to the main topic, I would like to acknowledge all the organizers, especially Professor Sangeeta Tiwari, Professor Ratan, and Dr. Ratan Upanda, who invited me actually when I'm visiting to my hometown in Kolkata this Christmas break. So thank you so much for all of your hospitality and arrangements. And my group, it's a little bit bigger group. We are actually 3 faculty members, including 4 postdoc, and 26 members are over there. My line manager, Professor Tapas Malik, and Professor Asif Tahir. My PhD supervisor, Professor P. Sujata Devi, she is currently right now in CSR NIIST Trivandrum. And all the grants that I have been granted to presented my work to do the research. So thank you, everyone. So yes, those who are not familiar with University of Exeter, which is in the England, particularly southwest of England, and you can see anyway, so it has a two campus. One is in Exeter, another one is the Cornwall. So Exeter is denoted by the letter E, and Cornwall is the letter C. And I'm based on the campus C, which is almost in the tail of the UK, just beside the Atlantic. Very beautiful campus, and this is our building over here. And our department is based on the second campus, but the main campus is in Exeter, which is almost 200 miles away from London. And also some features of our university is one of the top university in the world. In the latest Times Higher ranking, it is 143. And in 2023 QS World ranking, it is 163, a little degradation. And in the UK, it is 6th, and 9th in the Europe, and all the stuff. I don't know. And this is our department where I'm currently working. So if you just search in Google Solar Energy Department, University of Exeter, you will find more details. We are dedicatedly working on all the SDGs program denoted by United Nations, and we are proud to be member of the Future 17 program. And I'm one of the mentor of the Future 17 program, which is run by United Nations and QS, who is doing the ranking of all over the university. And you can see here is the hierarchical ranking that what are the SDGs program where we are leading currently in the world. And I'm based on the Environment and Sustainable Research Institute, where we are working different aspects of the nature, sustainable and environmental research, including energy development. I have been recently, a couple of weeks ago, to COP28 in Dubai, and there was a very interesting discussion over the climate change, and I think energy is one of the premium topic to be discussed over there. And you can see in the map that what is the currently net zero target of all over the world, and sadly or surprisingly, India is not listed. Anyway, but we are all struggling to get the only option is the renewable, who can solve the energy crisis and the carbon emission safety. Interestingly, in the recent recent COP28 and also in the G20 summit, which was in India, in Delhi, the old and the new paradigm, you can see that how the perception of the common problem solution has been changed. That previously people are thinking of how economically it can be viable, but now it is more about the policy, financing and institutional development, that how we can correlate each and every details, and that can be, for the better future. And still, if some people are still thinking that energy crisis or climate change is fake, there is nothing to do, I'm happy, I'm living my world, my life, my family is okay, then you are in dream, by the way. Anyway, so to save our future, it is very important to don't look over the memes. It's must look over, I would like to say it's definitely to be understand that what is the current situation of our environment. We, the humans, are not only the part of the society, there are other animals, other systems, other ecological backgrounds are there, so we need to think about that. So for very recent example of the climate change happened in India, and if you know about the Uttarkashi rescue, that's the biggest example. The next one is the recent Chennai cyclone. That's also another example of the climate change, how it is superiorly going on. Iceland disappearing from the Pacific Oceans. If you just go to the Australia and New Zealand, many islanders suddenly disappearing due to high rise level of the seawater, and continuous drought in Africa. That's also a very concern. So here comes the energy. We have to save energy. We have to reduce the carbon and all. So the best thing of renewable energy is the solar energy, because it is free, it is for everyone, it is common, easy to use, and free to use. We don't need to pay for that. But the thing is that how we can convert the solar energy into electricity or any other energy formation. That's the trick, that's the strategy as a scientist we have to develop. And here I would like to say that it's just not like solar energy means it's photovoltaic, it can be photocatalytic. My previous speaker speak about the solar water splitting. That's also another type of photocatalytic activity of utilizing sunlight. And another one is the photodynamic, there is a photothermal. So it's not about the light, there is a heat also including comes within the light from the sun. So how you can convert the heat into electricity using thermoelectric property. That's also an interesting topic to be discussed in the solar energy research. And to do everything, we need a good material. And here is the importance of a selective, exclusive, dedicated material which can do your exclusive solar energy work. This is our renewable energy department, and we have one of the biggest solar simulator and solar research laboratory in the UK, and including concentrated PV, PV glazing, BIPV, solar, a third generation photovoltaic, water splitting, and that's our research facility building. So what's on today? So everybody's talking about research, their achievement, their property, materials characterization, that's fine. But here I would like to see, or I would like to say that what is the added value? What I did for the society, what our research has done for the society, that is important. Publishing paper is a normal thing, but end of the day, how it is utilizing by the people for the society, that actually makes sense in real world application. And here is the come of dream, because dream is started with the analogy, and I still believe that nature and material has a very good connection. So for a quick example, if you just look at the electromagnetic wave and matter wave, they are very, coincidentally, they are very closer, very similar to each other. At the same time, the solar system and the atomic structure, just look at their outer structure, they are very similar to each other. So this gives us an impression, a sense, a flavor that from where we can start. So a material, if we change the color, a material, if it is, changes shape, a material, if it changes frequency, so that can be utilized to distinct property, and we can, enable to bring them for our application. So here comes the analogical study, and that's I believe it's very important. So material science is very important for the solar energy research, especially the light is very, the sunlight, it's called UV, visible, and NIR. But unfortunately, we lose the NIR radiation because there are no materials still evolved or there is discovered which can absorb the whole NIR region. So we lost a lot of light from the sun. We only utilize up to 2000 or 2200 nanometer light, and rest of the things just wasted. So we need to develop some material which can, convert all the light into the electricity. And that actually control the solar cells property, including their, open circuit voltage, different parameters. I'm not going to the details because everybody is not familiar with those, but how much light you are entrapping, that actually depending on the property of the solar cells. And for example, this is a quick example that how porosity and crystal structure is related. And if you just look at those pictures, that how porosity and crystal structure, there is a very big visual change about the transparency. And here is the importance of how you are developing and making the strategy of your material. Now think different, not very regular, just think different. There is a butterfly. So a butterfly wing can be utilized for solar cells. How that I can tell you in a couple of slides after this. So a butterfly wing is a natural inspiration from where we get the concentration of the light on the solar cells, which can generate a very high amount of power in a very single time. That's called the concentrated photovoltaics, and this is called the natural inspiration or the biomimicry. The another one is the photosynthesis, that like a leaf or like a natural plant, which is normally do photosynthesis. They convert light energy to chemical energy, produce ATP, we can also convert the similar principle from light to electrical energy. And I'm currently working on the smart window technology. So in future, we are developing a window where at winter time, we don't need to turn on a heater, or at summer time, we don't need to turn on an AC. So we can save a lot of energy and, of course, electric bill. Again, we are also working on some microbial solar cells, so microbes called some algae that can actually harvest energy from sun. So that's also a very interesting topic. Those who are working in biological sectors, they can have an interdisciplinary study with this. And more importantly, the solar waste management. Currently, we are recovering the silicon from the waste. Whatever the waste is producing for the solar panels, mostly they are silicon and silver, and how we can reproduce this. So this is my research topics today. I'm not going through all the details, but a very quick overview to all of you. So I'm currently working on photovoltaics, glazing, and solar thermal system, including passive cooling. Wastewater treatment and solar fuel we have just started in a couple of years ago, so a few of my students are working. And this is the system what we follow in our group, that how a research actually can work. So we call it potato research, which is very common. So just a quick overview, which is photovoltaics. And in photovoltaics, currently perovskite solar cell is the boss. So perovskite solar cells generating the similar efficiency in last 10 years. For silicon solar cell, it took almost 30 years. Can you imagine? So to get 20% efficiency, silicon solar cells took 30 years, whereas perovskite solar cells got the similar efficiency in 10 years. That is why perovskite solar cell is nowadays very common, those who are working on solar energy or photovoltaic research. So it's just the perovskite structure. I don't want to go to the more details due to the time constraint, but it's basically the depending on its stability and higher efficiency. And you can see from this plot that how the perovskite solar cells is actually going to commercialized with struggling with lot of environmental factor. But it has a lot of concern about stability, toxicity, cost, and scale up. So people are trying, and here is our attempt to make some added value to this particular research, where we have developed some carbon-based perovskite solar cells. Usually people use gold and silver. So they are very costly, and you can't do research gold and silver all the time. So as a replacement, we introduced carbon, and those carbon-based solar cells are showing some 15% of efficiency. And for more details, you can take a screenshot or go through my Google Scholar, you can get more information. But as an overall, I want to say that if you replace the gold and silver with carbon, it gets very high efficiency and high stability up to, the efficiency is up to recorded 15%. Similarly, we use the carbon from the carbon chute, which is usually we get it if you burn a candle or a lamp. And it's also very economically viable because you produce a lot of tons of carbon for a single, if you burn a single candle. So that's the thing. We change the temperature of processing temperature of making the fabricating the devices, and accordingly its performance value. And here also you can see the efficiency is pretty much impressive in between 10 to 15%. Also, we study some perovskite deposition in a different temperature, that how stable a perovskite solar cell, whether it's a single temperature dependent or a multiple temperature dependent. That strategy of research we have also done, and that is also shows that our carbon-based solar cell are quite impressive. We try to replace the perovskite, which is mainly lead dominate, and we replace the lead with copper, which is also cheaper and non-toxic, where the lead is very toxic for the environment. So this is the result, this is the scenario what we have what we have get. And you can see unfortunately we can't replace the lead fully with copper, but there is a partial replacement can be happen, and which can be controlled over the year and more precisely measurement. We merge our perovskite with the dye-sensitized solar cells, and where you can see that tungsten oxide play a very crucial role where they can enhance the efficiency of the devices, whether it is perovskite or DSSC dye-sensitized solar cells. So tungsten oxide WO3, if you use as a buffer layer, it can have an additive value which can immediately enhance your cell's performance. And here is the concentrated photovoltaics, that the example I have given from the previous slide from the butterfly wings. So in the butterfly wings, they use the similar concept, to concentrate the light, and you can generate different power and different heat from that wings. So similarly, we can't use big panels all the time because it costs a lot of installation and at the same time lots of space maintenance cost. To get the same efficiency for a very tiny solar cells, there is a concept of concentrated solar cell. So if you put a kind of lens, and it can concentrate the light at a very singular point, and it can generate very high amount of efficiency, a very high amount of power for a very tiny space. You don't need a very bigger panels. And this is our initial result, what we can see that, and we are one of the, we are the first report on this concentrated perovskite solar cells in the world, I would say, where you can see the perovskite solar cells have merged with the different types of concentrator which can generate a very high amount of power. So to get the similar power, you need this much of bigger panel, but we don't need if you use this type of optics. And we are right now commercialized and certified our solar panels, and we are working with the EPFL Switzerland, who are very famous for the photovoltaic research. And you can see this is our simulator where we are working and measuring our solar devices. And this is called the artificial sun, where we can change the intensity and concentrate the light according to the measurement. And this is the same, they see no optics, and optics, if you just look at the y-axis and check the values, they are quite different, and the distance are called the focal length. If you vary the focal length, you can see the power is also changing. And this is the heat stress analysis through the IR camera. And if you just look at the temperature, when it is concentrate the lights, there is an effect of temperature which can damage the cell, that I can show you how it can how it is damaging. And that is the analysis that we have done in collaboration with Toyota, because they are utilizing our cells in their cars in Germany. So that's the case that we have observed through this. And that's another review paper. We have collaborated with IIT Madras and Jadavpur University, Kolkata, where we have, make this understandable, that people should know that concentrated photovoltaics also another part of the research, and we can play with those optics. Now, this is my current research topic, which is the glazing and solar thermal. So those who are not familiar with glazing, glazing is nothing, it's just the window. In India, it's not important, but in European or Western country, window is a big factor of a house because it's colder country. So, and usually there is a double window system, or we call it a double glazing system. So 2 window glass pane, and in between either there is a vacuum or there is an inert gas. So all the window is actually placed like this. If you are traveling by any flight, if you look at the window seat, you can see this type of window is there. So that's called the glazed window. So this is my current research. So the idea is I need to develop a smart material. Our group need to develop a smart material. So utilizing those smart material, we can use those material, if we place those windows at the summertime, we don't need to install AC, and the winter time we don't need to turn on heater. So it depends, it maintains the room temperature. So that's the study that we have done, and if you just look at the curves, just look at the curves, that the room temperature and versus outside temperature, the red one is the out and the black one is the room. So how much the difference if we place this much type of glasses in our houses, so it can control the room temperature always at a very comfortable zone. Similarly, this is another work where we have shown the surface wettability study, switchable wettability study from hydrophobic to hydrophilic and again back to philic to phobic. And this is also a smart glazing material with indium oxide, zinc oxide based with paraffin. I started work with the smart glazing with, it's called the thermochromic and the perovskite. You can see according to the temperature, the window color is changing from yellow to maroon to black. And also you can control the room temperature if you just utilizing this type of window. You see the plot, the black one is the outdoor temperature, the red one is the indoor temperature if we install this type of window in our houses. Here we use some hydrogel material, which is organic material, and we inject it in between two glass pane. And you can see that according to the hydrogel properties, it changes its color. And if you know more about these details, I have many research blogs available in the internet. Please go through and have a look. And this is due to the time constraint, I'm just passing through. This is called the passive cooling. So I'm working on the dairy industry in the UK where we need to remove the heat stress from the cow body. By the way, cow having a lot of heat stress and that actually influences milk production. So as a result, either the cow drinks a lot of water or we need to install a big fan to cool down. So both are energy deficient process. So to do that, we have developed some graphene wallpaper. If you install it at the cow burns, they can extract the heat from the cows and it can store for overnight. And that is the wallpaper that we have developed, and you can maintain the milk production of the cows. So that is the way. And here I can see you that how the graphene actually help to maintain the temperature. If there is a very high temperature when you're concentrating the light, your solar cell might break like this. So to remove this one, we need a separate graphene coating over there that can actually absorb the excessive heat from the concentrated light. Also, we have utilized this type of wallpaper for different areas of the world, including Cairo, Japan, and Saudi, many places to check whether our system is actually weather adaptable to different, and we did with this building integrated research. This is all carbon-based solar cells where we have utilized the different allotropes of carbon. Remember, carbon have different allotropes, so that's the beauty of carbon. You can utilize different material. The source is same, carbon. So utilizing the different carbon allotropes and synchronizing them in according to their band gap, you get a device, and that can be a solar cells as well. That is also we first time reported, and you can see that's not, the efficiency is not too much good, but at least we have get the idea and the strategy that the different allotropes can be utilized for better efficiency in future. And that's also long-term 3 years installation results, that how if we are DSSC install, and that's a quick overview because we have just started the wastewater management, and my students have just done this work for her thesis. And we detect the BPA also from water. So BPA-free plastic is currently very popular. So we can detect the BPA utilizing some metal oxide photocatalysis. And that's our result, which is, you can see here, that's a zinc stannate nanofibers, so utilizing that. And that's also some carbon-based E. coli bacteria detection system in presence of light. You can see it can turn off, turn on mechanism. So immediately you can detect whether your water has a E. coli bacteria or not. And this is also some solar fuel research, the photocatalytic water splitting. My previous speaker already speak about that. And I work with the KFUPM Saudi Arabia and also a few universities in the Middle East where I'm working on the seawater depletion, because most of the people talking about water hydrolysis or H2O hydrogen generation from water splitting, mainly clean water, but we are more interested about the seawater. So that's it. This is our technology transfer. We have our own company called the Build Solar. We are running through our research, and also we are. I am a member of the WWF. We have installed 2,500 solar panel in the Sundarban area, which is the UNESCO site in West Bengal, and Pilkington, one of the largest glass company where we are working. I'm more interested in some interdisciplinary future work. If somebody interested in my research, please connect me. There is a multiple scope, and anyway, I'm available somewhere. Just last slide, the take-home messages. Just ask yourself before leaving the seminar, what would happen if we covered the Sahara Desert with solar panel? So that's the way that we think, and just look at the questions that sometimes may be interesting. There's panels everywhere. And I remember one 5-year kid asked me in a science festival about this question: do solar panels work at night by harnessing moonlight? It's very interesting, so just think and just take home message and think later. Okay, so thank you so much for your kind attention. Any question, I'm available everywhere. And thank you.
One quick question only. For double glazed windows in those houses, is there any deficiency of oxygen or air inside?
No.
Design is good.
Yeah, design is very good. Yeah, they are all leak free. Yeah. But we are trying to make it single glazing because double glazing is kind heavy. The weight is quite big. No question? Thank you.
Now we have a last invited talk of this session, Dr. Aurangzeb Khurram Hafiz, Jamia Millia Islamia. Is he here? Yeah. I'm just giving some brief introduction about Dr. Aurangzeb. He is presently the officiating director of Center for Nanoscience and Nanotechnology. He is also working as a professor in physics at Jamia. He has over 100 publications in various international and national journals. He has also given many invited talks at several conferences. His area of interest is quantum and nonlinear optics. So now let's invite Dr. Aurangzeb, please give a talk.
हो गया एक्चुअली ना सर पे पर ले कर अब बताओ चिंता भी कहाँ पर हाँ वही कर दिया भाई सर इसको ओपन कर देना पहले आप अपना यहाँ पर जाइए इसको डाउनलोड कर लीजिए
Sorry for the commotion. Good afternoon. I actually have a long association with Amity. It dates back to 2005 when I joined Amity Group as lecturer in Amity School of Engineering and Technology, Biswasan. 2006 onwards, I moved to Jamia Millia Islamia, where I taught in the Department of Physics till 2017. Before I shifted to Center for Nanoscience and Nanotechnology. Since then, I have been working on nanophotonics, nanomaterials, and nanostructures. So I would like to thank Professor Ratan, and I have my colleague, Professor, sorry, I got Sachi Chawla, Professor Chawla, who is a good author and has written several books to my knowledge. So I thank all of them for inviting me, giving me an opportunity to come here and present. The talk, the title of my talk is very specific actually. It has to do with perovskite material. Dr. Anurag was just before me, he was talking about, discussing about the same. Incidentally, he also happens to be from Kolkata, from which I also belong to. So the idea of this particular structure is such that, of course, we need to build something which can be more efficient in terms of optical applications. Precisely, if we talk about optical applications, we refer to either optical detectors or solar cells. The target for today, for my talk, is around solar cells. So we need to build up active layers, which can be much more beneficial. So we should have an active layer that is can be much more efficient than your typical silicon-based active layers. So my discussion will feature around nanomaterials, solar energy, perovskite, then the experimental details, which I won't like to go into the details, then will perovskite challenges and solution, before I talk about our results and discussions. So as every one of you in the two-day conference, nearly all must have talked about the nanostructures, nanomaterials, and etc. So why it is important? Why the nanomaterial is important? Because what we see in bulk, we see a different regime, a different altogether properties when we go to the nano regime. Why it happens so? In a rudimentary form, if I have to put, surface to volume ratio increases hugely. Now, if I say surface to volume ratio increases hugely, then why are we at all bothered about properties? So then you have to think about how the electrons behave when they are at the surface, when they are in the bulk. So precisely the constraints or the confinement of charge carriers results in change in the physical properties, and that evolve novel materials or tailored materials that today is highly in use. So this is one of the example. If we decrease the size, how the ratio of surface to volume increases. These are the size description of nanomaterial right from centimeter when we reach to 1 angstrom. So the different materials or the different species that we see are located in different domains of sizes. If we talk about nanomaterials, we tend to classify them into several domains: 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional. So mind that this 3-dimensional is not a bulk that we are talking about, but a 3-dimensional structured material. So there is a difference between when I call it a bulk material and when I call it a structured material. So this is a structured nanomaterial that we are talking about, and 2D material which is in vogue today, for example graphene sheets or MOSE2 2D structure. This is very popular nowadays. Nanowires are also picking up, and of course 0D material quantum dots you must be familiar with. So why are we concerned about solar energy? The solar energy we are concerned about is because that is one of the energy which is abundantly present, but we are unable to utilize it to the fullest. So there are several government schemes that have occurred in India trying to encourage this solar energy harvesting. So our major concern is how can we harvest solar energy with high efficiency. Okay, this is a rudimentary structure of a solar cell. So there are two things. Rather, when we talk about novel materials and when we talk about how can we enhance the efficiency, we either talk about the absorber layers or the kind of trap layers that we can create in order to enhance light matter interaction. Our goal for today is to create active material of perovskite, tailored perovskite I should say. That I'll talk within a few slides why I'm talking so, tailored perovskite, that can give or that can have a high efficiency in the optical domain. So perovskite is one of the novel material that has originated, let's say, some 10, 12 years back or 13 years back, in which there are 3 parts, A, B, X3. A monovalent inorganic cation, B divalent metal cation, X can be any halogen that binds the two. Now the properties that it exhibits is direct and wide band gap, low exciton binding energy, high ambipolar transport of charge carriers, and high defect tolerance. So in general, we can have any modification of such a structure. It's not necessary to keep ABX, we can have ABX6 and so on and so forth. So we can have modification to this structural formulation also. But the target should remain the same, but the properties it should exhibit is this. So band gap engineering in case of a perovskite is very, very efficient depending on the kind of halogen that we use. So it can be tailored accordingly. In this case, in our case, we have used cesium lead bromide, CSPB BR3, and that lies in the region which we can say mid region of the visible range. Experimental details I'll talk in a few slides. So we have used basically, despite several options, we have used hot injection method in which we efficiently could make the particular compound. Okay, as I said that in a matter of 12-15 years or 12-14 years, the idea of perovskite has grown in leaps and bounds. So for example, from 3.8% efficiency it has shown in 2009 to 26% efficiency it has shown in 2023. A theoretical calculation says, a formulation says that we can have an efficiency up to 66% with a perovskite material. But that's of course a theoretical formulation. So it has grown in leaps and bounds. But then there are certain challenges it has. The most important one is the stability concern. So if we have a humid environment or if it's exposed to air, we are not very sure how long it will remain without any degradation in the structure. So one of the strategies that we have used to sort out this particular problem is by combining CSPB BR3 quantum perovskite quantum dots with your graphitic carbon nitride and nanosheets. So we have basically decorated the graphitic carbon nitride nanosheets with the CSPB BR3 PQDs. So this is the work that we have done, and this is the type of experimental setup that we have utilized to finally reach the targeted heterostructure or composite, you may say, of PQDs, PBBR3 PQDs and graphitic carbon nitride nanosheets. Okay, from the 10 images of that particular composition, and on one hand we have CSPB BR3 PQDs, what we observe is the average dimension. In case of PQDs, that is the pristine PQDs, it's 11.23. But when it's in the composite form, the average dimension is around 22 nanometers. And your interplanar spacing in case of pristine PQDs is 0.58 nanometers. That along the 110 plane. And in case of your composite, together with this particular dimension, we have another dimension of 0.31 nanometer along the 002 plane that signifies, or that talks of validates the presence of your graphitic carbon nitride nanosheets. Okay, the XRD data basically shows that in our composition we have all the necessary peaks that we need for CSPB-BR3 and CSPB-BR3 GCN composite, except that only the intensity in the composite is lower than what we had in the pristine structure. Your X-ray XPS data shows the composition, presence of all the elements with all the particular bonds, with the binding energy of all the particular bonds. So that is that clearly shows that our structure that we have constructed, or our structure that we have made, is perfect. Now coming to the target that we had while making such a structure, we did steady state optical measurements, we did absorbance, we studied the absorbance, we studied the PL emission. In the absorbance we saw there is a slight change in the peak, basically a blue shift of around 4 nanometers in the peak, and slight lower in the intensity. PL we observed quenching, which we actually expected, and around 20 milli electron volt of rise in the energy gap. Also, the time resolved decay characteristics show that of the pristine PQDs, the average lifetime was 5.08, but when we had a composite, the lifetime increased to 8.94 nanoseconds. This was the basically structure of the charge transfer that takes place from your GCN to your CSPBR3 PQD and from your CSPBR B3 PQD to GCN. Now this shows that the basically the valence band of CSPB-BR3 will be populated in case of the composite, while the conduction band of GCN will be populated in the composite. So the DFT calculations actually validated what we had experimentally found, and the GCN nanosheets mainly contributed to the conduction band minimum, while the valence band maximum is contributed by the CSPB-BR3 PQDs. That's what I was talking about the last time. Now electrons separated will reside in the conduction band of the GCN, while holes separated will be residing in the valence band of the PQDs. Of course, this will lead to the charge separation that we had expected, and the time that it takes, the delay occurs because of this charge transfer. So while observing these, we have performed ultra-fast transient absorption spectroscopy, where we used pump pulse and the probe pulse. The pump pulse, we had two powers, 0.25 microwatt and 0.5 microwatt at two particular wavelengths, 350 nanometers higher frequency and 450 nanometer of the lower frequency. Now the pump pulse was responsible for the ground state bleeds that occurred. Okay. There were radiative path decays that was involved in the species. So our species 1 is basically your PQDs, and species 2 refers to basically your GCN nanosheets. So this is the charge dynamics that we were expecting, and what we got is that a charge transfer from the PQD to the GCN in case of the conduction band, and a charge transfer from the GCN to PQD in case of the valence band. And this interaction involved bi-exciton, creation of bi-excitons, this particular interaction of charge transfer from one material to the other. Okay, this is another plot that we have observed in case of 350 nanometer of excitation wavelength and 0.25 milliwatt pump power. These are on A and C is the other pseudo plots, while your B and D, in which in B we observe that probe pulse induced excited state absorption. So there is a conversion of PIA to GSB due to the bi-excitonic induced Stark effect, and there is in the plot D, if this is the earlier was the case for CSPB-BR3 pristine structure, while in the composite we observe that enhancement of PIA. Okay, so it is associated with bi-exciton formation. So obviously enhancement of PIA will be associated with that. The prominent GSB is due to the interband transitions. So there is interband and to intraband transition. So PIA is mostly dominated by the intraband transition, while GSB is dominated by the interband transition. Okay. This is another plot that we have that actually refers to the same finding. I will not go into the pseudo plots. Okay, here this is the detailed results of the time delay that occurs for different combination of pump pulse, probe, and probe, as I did not mention the details of a probe. Probe is basically white light that we use, having range from 480 to 720 nanometer. So this particular plot actually says one thing, that your presence of the graphitic carbon nanosheets, carbon nitride nanosheets effectively helps in slowing down the cooling of hot carriers. So we have hot carriers which are in the higher higher energy states, and that stays in the trapped states because of the presence of the nanosheets. So these are some of the details of the changes that occur because of the presence of nanosheets in the composite. So for example, if we take about P average, so it's like a jump from, in the pristine case, 370 picosecond to 844 for particular higher wavelength, and 0.25 nanometer of for a particular 350 nanometer wavelength and 0.25 milliwatt power. Then this jump, this difference is lower in case when we have a 450 nanometer, lower frequency pump, and 0.25 milliwatt. So again, at a higher pump strength, at 350 nanometer, we have a jump from 327 to 676. So it's a huge time delay that occurs. Okay, and same if we have a 450 and 0.5 nanometer, 0.5 milliwatt power. So there's a difference is low. So because of the presence of your graphitic carbon nitride nanosheets, the time delay or the occupation of the charge carriers in the trapped states increases by highly. So the same thing from a different perspective is given here. So you can see the difference in the time between the pristine and the composite. This is the charge carrier transfer mechanism that we were discussing about. So if the pump power is high frequency, then there is a chance of bidirectional shift. But at lower frequency, that bidirectional shift is not there. It's only in the one direction it goes. So in conclusion, I can say that when we decorate the PQDs of CSPB VR3 perovskite over GCN nanosheets, we have a time delay in the decay of the excited states, and this increases the stability of the overall stability of the structure. These are some of the work that we have published in this particular regime, in this particular area. And I would like to thank my collaborators from JNU, NPL and IIT for this particular work. This is my student, Dr. Vandana Nagal. This work was a part of her thesis. Thanks for your patience.
Thank you.
Thank you for the informative and interesting sessions. I'm sure it will be very beneficial to all our listeners. We would now like to invite our delegates for oral presentation, 8 minutes presentation and 2 minutes for question and answer. Judges for oral presentation are Dr. Shashi Chawla, Dr. Arindam Modak, Dr. Rohit Verma. I now call Mr. Abhay from Sharda University for his oral presentation.
So, good afternoon, everybody. So, our work is about the excellent piezo photocatalytic performance of bismuth ferrite oxide with nanocomposite of graphene oxide, graphene, multi-wall carbon nanotubes, and reduced graphene oxides nanocomposite. We are here on behalf of the Dr. Sangeeta Rawal from Sharda University. My name is Abhay Singh and I am a student of BSc Physics program at Sharda University. So, in this discussion, we will be discussing about the basic principles and concept of photocatalytic activity and piezo photocatalytic activity. Then we will go for our work, the synthesis part for the nanocomposites, and with the results of XRD, FECM, TAM, and the dye degradation by UV visible spectroscopy. And with the references, we will summarize our work. So, photocatalysis is the process of degrading the pollutants present in the environment. So we have taken here the example for titanium oxide. So when the solar radiation radiates on the titanium oxide substrate, it emits the electrons and produce holes. These electrons reacts with the oxygen present on the surrounding and creates the superoxide radicals, and holes reacts with the moisture present in the surround to produce the hydroxy radicals, and these radicals acts as the detergent for the surrounding environment and purify and decompose the pollutants present in the surrounding. So these are the applications of photocatalysts: the water purification, environmental remediation, chemical synthesis, deodorizing and air purification, and this is the very potential process of making the purification for water and as well as the air. We have also worked on the piezo photocatalysis. So in this case, the piezoelectric effect is also included with the photocatalysis process. In this case, with the help of vibrations or bar sonications, we create the piezoelectric, and this emits the electrons and produce holes, and the same oxidation and reduction reactions goes through it and produce the radicals which reacts with the pollutants and decompose them. In this case, we have taken the bismuth ferrite oxide because due to a suitable bandgap 2.2 electron volts, it is very suitable for photocatalytic activity. So this is our synthesis part of BiFeO3 with graphene oxide, reduced graphene oxide, multi-wall carbon nanotube, and graphite nanocomposites. So we have taken bismuth nitrate and iron nitrate as the precursors. With the double distilled water and the nitric acid, we have prepared the two solutions, and then mix this solution with the tartaric acid and leave it for the on the hot plate stirring at the temperature of around 60 to 80 degrees Celsius for around 24 to 48 hours. This produces the gelation like solution in the beaker. Then we put this gelation gel type structure in the muffle furnace at the temperature of 500 degrees Celsius for around one night to calcination, and then we can get by the piecing with the mortar and pestle, we can get the BiFeO3 nanopowder. Then we have added the measured amount of carbon allotropes like graphene oxide, reduced graphene oxide, carbon nanotubes, and in the prepared BiFeO3 nanopowder. And by the help of bath sonication, we have prepared the homogeneous mixture of the solution, and then by dried up, we prepared the nanocomposites. These are the results. This is the XRD results. So you can see the different peaks and the planes present in the BFO. And these all peaks are coming from the only bismuth ferrite oxide, because the nanocomposites are present in the amorphous form. So the XRD can't recognize them in this case. So you can see the different planes 0, 1, 2, 1, 0, 4, 1, 0, different lattice planes are present in the nanocomposites. These are the FTIR results. So there are carbon and oxygen and carbon and hydrogen bonds are present in the nanocomposites. The first two peaks are coming due to the BiFeO3 around 500 per centimeter reading. These are the FSM results. You can see in the case of BFO, the particle type structures. In BFO GR case, the sheet type structure, you can see the sheets of 1 to 3 layer of graphene. And in the multiple carbon nanotubes and RGO, these are the structures. Time analysis, you can see in the case of multiple carbon nanotubes, the tube-like structures, and in the RGO case, the sheet-like structures. The diameter of these tubes are around 50 to 100 nanometers. These are the elemental mapping of BiFeO3 and MD, MWC and T and RGO nanocomposites. This is our main work, this piezo photocatalytic results. So we have used bath sonication and light lamp to by using the UV visible spectroscopy, we have gained these results. So in the case of BFO RGO, you can see the most degradation within the 2 minutes of bath sonication with presence of light. The whole dye, we have used the dye as a rhodamine B in this case. So this rhodamine B dye has fully decomposed within the 2 minutes of bath sonication with light. So these are our results with BFO GO, BFO GR, BFO multiple carbon nanotubes, and bismuth fluoride oxides with reduced graphene oxide. This is also showing that in the case of RGO, the decomposition of RHB is maximum, and then in multiple carbon nanotubes, and then GR, and then GO. These are results for different dyes. We have worked on for methyl orange and methyl blue. So this is the photocatalytic result. So within 25 minutes of light and bath sonication, the whole dye is degraded. And in the case of methyl orange, within the 25 minutes, the degradation of light, you can see, degradation of dye, you can see by the help of this graph. Thank you so much.
Why your graph like data showing better result in case of RGO only?
Because in the case of RGO, we can see I think the band gap structure for BFO. So if we take the valence band gap between the valence gap and conduction band is in the case of BFO, so 2.2 electron volt. In the case of reduced graphene oxide, it is showing better results.
GR is graphene?
Yes, sir, graphene. Yes, sir.
What is GR?
Graphene.
Why it is not same GR? Both things are same.
Because the carbon and oxygen atom ratio in the case of RGO is more than the GR.
One thing, how will you determine the superoxide if present in your catalyst? How will you determine it? Which experiment you will use?
How will I determine?
How will you determine?
Sorry, sir. Which experiment and in the sense, sir, experiment in the sense?
Yes, any experimental
Sir, we have taken a bath sonication, and we have prepared the solution, the nanocomposites, and we have prepared the solution of RHB, rhodamine B, and then we prepare. Okay.
Thank you. I now call Dr. Sharon J. Paul from CSIR National Physical Laboratory, New Delhi.
A very good evening to the members of the jury and teachers and my dear colleagues. Myself, Dr. Sharon Paul, CSIR NPL. The topic of my presentation is exotic carbon nanomaterial PDMS derived ultra-sensitive lightweight wearable strain sensors for a wide range of human motion monitoring. In my introductory slide, I would just like to give an overview about the material that is being used as the wearable sensors. So as we know that humans have undergone a series of evolution defined by the material that is being used, starting from the Stone Age, the Bronze Age, and we see that today carbon nanotubes and composites are playing a transforming role in transforming the present and the future age, that is the material design age, because we see that they are being used in almost every sector of life, maybe roadways, medicines, medical equipments, sensors, building materials. Sorry. So what is a composite actually? A composite is a material that is derived from two or more constituent materials. When combined together, they give different physical and chemical properties other than that of the... Should I take that mic? Okay, sorry. So what is a composite? A composite is a material that consists of two or more constituent materials with different physical and chemical properties. When combined together, they give another material with characteristics different from the individual components. Now, it consists of a guest matrix and consists of a reinforced material. So in my present study, I have used polymer as the guest matrix and the reinforced materials is the carbon nanotubes. You all must be aware what is nano, but just to fascinate you more, how small is nano? Imagine a baseball bat that is 1 meter. Now, a nano is 1 billionth of 1 meter. Why do we use nanomaterials? It is because when we move from the bulk material to the nanomaterial, the properties change drastically. Now, the main goal and the purpose of my study was to develop a suitable lightweight, high-strength polymer nanocomposite by incorporating carbon nanomaterial in very less amount to enhance the electromechanical attributes and create materials with high-end applications in wearable sensors. Now, when we talk about wearable sensors, there are certain problems, there are certain concerns that come in. What are those top concerns? It being the poor sensing mechanism, the limited range, they are very expensive, the sensors that are available, and they are not able to detect diverse human motions, they are bulky, they are heavy, and they have excessive power consumption. Now, the solution to is to develop such a material that is ultra-sensitive, that has wide range of human motion detection, that is cost-efficient, that is multifunctional, that has long lifetime, and is highly durable. So, also, the main concern here comes with the patients with Parkinson's disease, the hand tremors in patients with Parkinson's disease. Now, this requires a very low detection of the low strain detection. So, the sensor that we developed was capable of monitoring even the very lowest strain and also regular continuous monitoring of the hand tremors in Parkinson's patients. And it is a very sustainable and a very cost-effective solution. And it is skin-mounted, so it is skin-friendly. And also, the very fascinating and interesting feature is that it can also help to distinguish between essential and intentional tremors in patients with Parkinson's. So CSIR NPA, along with National Institute of Immunology, is working on this project where we are testing the Parkinson's disease over an animal model. The material that I used, everybody is well aware of the carbon nanotubes. Carbon nanotubes, they are the sheets of graphene that are rolled up at specific axes. Now, why do these graphene sheets roll up? Because they have dangling bonds, making the sheet very unstable. So they roll up into cylinders that are called as carbon nanotubes. But what I'm talking here is not any random carbon nanotube. What we are talking here is a very exotic architecture of carbon nanotube. Now, the exotic architectures are like vertically aligned carbon nanotubes, where the carbon nanotubes are aligned in a vertical direction. Then there's horizontally aligned carbon nanotubes, radially aligned. There are CNT foams, there are sponges, there are CNT yarn, hydrogels, bucky paper, and aerogels. So in my particular study, I have synthesized and studied vertically aligned carbon nanotubes, bucky paper, and CNT foams. So this is a synthesis of the multi-wall carbon nanotubes. If anybody wants to ask about it, I can definitely discuss it later. I would further move on to the slides because I was asked to conclude in 5 minutes. So bucky paper, the BACNT was synthesized using CVD setup. Bucky paper was synthesized using ultra vacuum filtration technique, and PDMS sponge was synthesized using drop casting method over a PDMS sponge that was synthesized using a sugar template. So this is the comparison of the sensors that are available in market and also the ones that I have synthesized. So as you could see that VACNT thin film comes out to be the best result because it has this response and recovery time of 12 to 90 milliseconds, and stability is over 10,000 cycles, and the sensing range, as you could see, is 0.004, which is a very low detection range, up to 30%, and covering all human motions in this category, and the sensitivity is also quite high. These are some of the morphological studies where you could see the vertically aligned CNTs and also the ones that the composite after the incorporation of the PDMS into the VACNT. Then there are the mechanical, electrical and hysteresis study which show that the sensor is very mechanically stable. As you could see the tensile stress and the strain curve, the loading cycle, it grows on very linearly, and when it returns, the unloading cycle, it is without any plastic deformation. So showing that the sensor is very mechanically stable. And also the hysteresis that is calculated has a very consistent value, and the value is very low. These are the piezoresistive and electromechanical studies where the mechanical deformations have been transduced into electrical signals and recorded when the resistance change. So as VACNTs, they are densely packed, but when you stretch it, the conductive networks move apart, thereby increasing the resistance, and that is how we measure this resistance of the surface. And as you could see, the gauge factor here is telling about the sensitivity of the sensor, which comes out to be really high, that is around 6,000. Then as you could see, around 10,000 cycle, the sensor is very stable, very synchronized signals, and when you pick up one signal and calculate the response and the recovery time, it gives you 12 milliseconds of response time and 90 milliseconds of recovery time. Now the application of the sensor. This sensor was adhered onto the wrist of an individual measuring the pulse rate. Now as you could see that the systolic and the diastolic pressure peaks could easily be observed. And also before the exercise and after the exercise there is a difference. All right. Yeah, and also this sensor was again then put on for vigorous human motion detections, including finger bending, wrist bending, walking, sitting, jogging, and we could see that there are well synchronized signals, yet we could distinguish between the different signals of the different motions. So this single sensor was capable of measuring wide range of human motion, and also this could be used for measuring even the lowest strain for patients with Parkinson's disease, and it has further applications. This work was covered in Science Monitor. I think the audio is not here. So it was covered in India Science and Science Monitor. And also this is a live demonstration, which I think the video is not working. This is a live demonstration over an individual for breathing pattern and for finger bending. This work was also covered as research highlights in Nature India. And these are some of my key publications in highly reputed journals. Thank you all for giving a patient hearing to my presentation. Thank you. I'm open for questions.
How you ensure vertical alignment of carbon nanotubes are there, and how it can be done?
So that I will tell you on behalf of the growth, how we did the growth. So what we did was we took an SiSO substrate, and over that we deposited aluminium as a shadow mask technique, and then over that iron catalyst was deposited, and so that on the pores of the aluminium the iron was deposited, and then over that iron catalyst the CNTs were grown in the CVD setup. So the vertical alignment was there. I have the same images, and by controlling the time and the duration in the CVD, we could control the height of the forest. So what I got was around 8 microns till 1 millimeter. So that is how we could control the growth, and that's the alignment how we could see. Thank you. Sorry? Sir, as we compare to the ones that are available in market, you know, if you see the power consumption that they do, and also if you see that how much raw materials involved, here only a very small amount of carbon nanotubes you are taking, and it is causing a wide difference. So that is how it is very cost effective.
You have not shown in these years less than 5% strain. Actually, you are talking about the body movement.
Right. So yes, the strain that we were talking about, that the sensor measured about 0.004%. So that was when we actually subjected to tensile strain and then measured it. Also human motions, if you see the frowning and all, this comes below 10% of the strain. The frowning, I have shown that I was asked to move it. Yeah, but there are other motions like breathing. Now, breathing doesn't come up to 30% strain. The breathing pattern comes below 10% strain. Also, the hand tremors that we are discussing about the Parkinson's patient is not beyond that. It comes within 10% of the strain. And what I am talking about, 0.004%, that was still measured by using the tensile stress strain setup. So that is how we got to know that that is the minimum detection range. Thank you.
Thank you very much. Now I call upon Dr. Rakhi Grover from Amity University for her presentation. I request you all to kindly maintain silence.
Good evening all. I'm going to present on my work, Characterization and Ammonia Sensing Properties of Tin Sulfide Silicon Nanowire Heterojunction Device. First of all, let me tell you why I chose tin sulfide thin films, because the semiconductors from 4 to 6 group have been drawing much attention in optoelectronic devices, and in recent years tin sulfide especially is attracting great interest as an absorber layer in photovoltaic because of its optical band gap compatible energy gap, great optical absorption coefficient and high optical transmittance. SNS is a p-type semiconductor which is comprised of cheap and non-toxic elements which can crystallize in cubic as well as orthorhombic structures. It is reported to be having a band gap ranging from 0.9 electron volts to 1.8 and has an absorption coefficient above 10 raised to 4 per centimeter. And in detail, if I say, tin sulfide thin films are attracting great interest in solar absorber materials as well as another optoelectronic devices like photodetectors and thin film based gas sensors. Theoretically, it has been predicted that maximum power conversion efficiency of tin sulfide thin films for single junction thin film solar cells could reach a value of 32%. However, in practice, only 4.4% has been achieved so far. It has also been used as a substitute for platinum, more specifically in dye-sensitized solar cells, because the cost of platinum has to be reduced for reducing the cost of these kind of solar cells. So, use of tin sulfide is becoming more widespread and includes applications in photodetectors, lithium-ion and sodium-ion batteries and sensors amongst others. And if we discuss about the thin film deposition of this semiconductor, we can have electrochemical deposition, RF sputtering, spray pyrolysis, chemical bath deposition, vacuum thermal evaporation, and other methods also. Out of these methods, chemical bath deposition is far the simplest in terms of experimental setup because of its convenience, low operating temperatures, and relatively inexpensive tools. In this method, the special thing is that because we can control the morphology of the thin films by controlling the precursor solution, growth conditions, and the temperature of deposition. This image shows you the basic technique in chemical bar deposition. Here, chemical bar deposition basically relies on creating a solution such that deposition changing from an aqueous to a solid substance. Metal salt precursors are all added into water to form an aqueous solution, and we can control the temperature, pH and concentration of the salts, which are adjusted until the solution is in the metal stable supersaturation state, that is until the ions are ready to deposit on the substrate. So as soon as the substrate is introduced, which acts as a catalyst for this nucleation, and the precursor ions adhere onto the substrate forming a thin crystalline film. In the present work, what we have done, we have used plain silicon, p-type silicon wafers as a substrate and silicon nanowires as a substrate also. This is just showing you the all process used here. We have demonstrated the synthesis of tin sulfide thin films by chemical bar deposition using tin chloride and thioacetamide as a tin and sulfur sources, which can be used to deposit the tin sulfide thin films using triethanolamine as the complexing agent and ammonium hydroxide alkaline bath. This is the detailed procedure how it was deposited. And the silicon wafer with resistivity and 1 to 10 ohm centimeter and 380 micron thickness with P-type properties were used as a substrate, and silicon nanowires were also used as a substrate in comparison. The clean substrate were fixed vertically in the freshly prepared chemical baths and were placed in water bath maintained at 30 degrees Celsius for 4 hours. This temperature as well as time of deposition was first optimized and then used to compare the behavior of nanowires as well as the plain silicon substrate. So this image shows you the SEM and EDX analysis of tin sulfide films deposited on silicon substrate. The EDX pattern also, the percentages also confirm the presence of tin sulfide in the films, and the image also shows the uniformity of tin sulfide deposited. This image shows the SEM and EDX analysis of tin sulfide deposited on silicon nanowires as the substrate. The same images clearly depicted the deposition of tin sulfide thin films uniformly on silicon substrates and nano-sized clusters deposited over silicon nanowire substrates, and the optimization of the precursor solution and the mechanism involved in CVD technique can result in perfectly controlled morphology for optoelectronics. This has to be further optimized for better applications, and this has been used for ammonia sensing properties. This graph shows you the heterojunction device made using silver contacts on the top as well as bottom on silicon tin sulfide thin films and silicon nanowires as a substrate and tin sulfide thin films over that. All these graphs show that as the silicon nanowires are used as a substrate, the current obtained was greater because of the increased surface area. And secondly, as the ammonia was introduced, it shows greater current densities, greater current values in the presence of higher intensity of ammonia. So the films deposited over silicon nanowire substrate exhibited increased current values as compared to plain silicon substrate, and in the presence of ammonia vapors, both the films showed increased current values. Thanks. Special thanks to my group members, Dr. V.K. Jain, Dr. Kanchan Saxena, and Dr. Sucheta Sen Gupta ma'am. Thank you all.
Thank you very much. I now request Dr. Bhanu Pratap Singh to felicitate Dr. Vinod Kumar Jha with a memento. I request Dr. Bhanu Pratap Singh to felicitate Dr. Vinod Kumar Jha with a memento. So I request Dr. Bhanu Pratap Singh to felicitate Dr. Anurag Roy with a memento. I request Dr. Bhanu Pratap Singh to felicitate Dr. Aurangzeb Khurram Hafiz with a memento. Dr. Aurangzeb Khurram Hafiz. Thank you very much. We now proceed with the valedictory session. Thank you.